We will wait for a couple of minutes and then start. I think this you are aware of the schedule change, right? Friday to move to Sunday, and we just plan to have lunch here that day, so that you do not face any other problem. Okay. So, we will have lunch here itself. Okay, I think let us start. Okay. So, good morning everyone. Today I am going to talk about mostly power side channel attack and its protection in the first half, and in the second half I will try to talk about how do you build ML accelerator or whatever the AI system you build for cyber security and all, how do you build them, right. If you want to map them into FPGA, what will be the easiest way to do that, right. So, and then I also talked about once you have this ML hardware running and what kind of security risks are there when they are running on edge devices, and what are the way you can attack them and how what is the protections on that, right. So, this power side channel primarily on the hardware side. Professor Mishra was talking about various software attack, and there the primary objective was to get access of your system, right, and then try to get this information. So, here primarily these power side channel attacks have been done on this cryptographic hardware, right. So, you know this AES and all these cryptographic algorithms, they are theoretically proven, they are very secure, right. But once you implement them in hardware, there are other information you can actually access when it is running, that it is running on the devices, and from those extra informations you can actually get the key. So, here the attacker objective is to get the secret key what was there in this AES algorithm. And you understand that, as Professor Mishra was saying, that the security community, the algorithm is known to everyone, right. What algorithm is known to everybody, knows what is happening there, only thing is not known is the key. So, the objective of the attacker is to get the key, secret key, then he can actually he can get the actual message, right, not the encrypted message. So, in today I am talking the first half of this lecture, I will talk about how do you actually do this power side channel attack. I think many of you do not know, you all assume that it is possible, right. But I will try to go through the AES algorithm, and if you, I mean how do you actually, what are the steps you should follow, so that you can actually get the key from the AES implementation running on some devices, right. So, I will first half of this talk, I will talk about on this power side channel attacks, and then what are the counter measures is has been implemented and how do you protect even those kind of against this power side channel attack, right. That will be the first 1 hour plan. So, there are various side channel attack possible. One is power, as I mentioned that your cryptographic things are running on a device, and somebody is measuring the power from some interesting point of your design, and then do some analysis and they can get the key. So, remember here you can control the inputs, right. You want to encrypt some text, right. So, you can give any text as you want, right, and then you can get the output. Only thing is that you cannot get any internal information, any internal values, because you have no access to the internal component of the design, right. So, you effectively only get the output, and input is on your control, and only extra information you are going to get the power, for example, in power side channel. There are many other kind of attack possible. One is fault injection, is basically try to insert some fault in your circuit, right, by either increasing the temperature somewhat so that the bit get flipped, or maybe by say some voltage, ion beams or electromagnetic fields. So, there are many way people try to change or create fault into your design, and as a result your output will be not the exact one, right. And then they know what is the encrypted, because if you run the AES or correct AES, what is the correct value will come, right. So, now you know what is the corruption and what is the correct value, and be doing some analysis you can identify the key. So, this is another way of doing this attack. Timing, as Professor Mishra was discussing in the last class, that many times our algorithms are the if else loop are not basically evenly, the number of instructions in the loop, the if branch and else branch is not the same, right. So, if you, and most of the time when you write your program, that most of the condition true most of the time, right. So, that means the number of time it goes through the if branch and else branch is not the same, right, and the number of clock cycle needed to execute the behavior if it goes through 10 if else, if loop and else loop is not the same. So, if you run for multiple number of inputs and you see the delay, the time of execution, you can guess whether the if branch happens or express will happen, because the algorithm is known to you, right. So, how many instructions there in if and how many else you know. So, that is kind of the timing attack, right. So, there are also other very sophisticated like acoustic, various kind of sounds or any noise you can actually collect from the device it is running the cryptographic algorithm, and then you can do that. And also there are cache, so from the cache misses, number of cache replacement, all those from those values you can actually also can guess what is the key value, right. So, and electromagnetic is also is part of this, right. So, this is here also. So, these are the various way of attacking a hardware implementation of an cryptographic algorithm, but in this lecture I will primarily focus on how this power attack happen. Okay. So, please feel free to interrupt me and ask any questions. So, this power side channel attack, as I mentioned, you have this cipher is basically your algorithm running. You can control inputs, you can actually this control chip can give any input clock, any frequency and everything, and you can measure the power, right, what is happening. So, this is the kind of framework. Okay. So, how do you do that, right. So, basically if I give you a implementation, what are the steps you should follow or the attacker will follow to get this cryptographic keys, right. So, these are the 4 steps effectively of the algorithm or the kind of steps the attacker should follow for this attack. The first thing is that you find the point of interest in the design. Not everything is interesting, you need to identify which point of the design or when which part of the algorithm is executing. So, I want to get the power from that part, right. So, you identify what is the point of interest for you, then you execute the algorithm on that devices for various inputs, right. So, and then you collect the traces at that point, right, and then you basically have some selection parameter, I will talk about that, through which you can expose the key. Okay. So, these are the kind of steps we should follow. Before going into this power attack, because I am going to talk about how to do in AES and it is for 128 bit keys, I will just give brief overview what AES does. So, AES has basically rounds. Okay. So, you have basically a round which has substitute bytes or S box operation, shift row, mix column and add round key. So, this happened 10 times, right, 1, 2, 3 to 10, right. So, this is the same set of operations happening here, and before that you have this add round key. So, this is the plain text, the text you want to encrypt, right, and the key is coming here, and key is basically the thing is the secret, I want to get this value. So, what is add round key? It just does the XOR between the plain text and the key, it is just the XOR operation. Sub byte is basically you access a specific S box, the value is well known, you replace those that cipher text, it is called cipher text, with the specific value from that array, right, S box based on this value, right. So, it is basically you access, this is the access, the index of that array, and you replace that with this. I will give an example also. Then shift row is basically you have the rows you shift them in a specific predefined value, right, either shift row by 1, 1, 2 and 3, something like this. Mixed column, you multiply the column with some specific values and then again you do the add round key, right. So, this is the kind of 4 steps or operation in one round, and this is going to happen for 10 rounds. Only in the 10 rounds one of them is not happening, is the mixed column, right. This is well known algorithm, and then you get the encrypted text, and this is the reverse direction, right, the same operation in reverse direction you do. So, now what is the interesting point in this algorithm where we should do the mount the attack, so that I can get the key. So, what I will do effectively, I will basically try to measure the power, right. So, this is the kind of power trace corresponding to one text. You give one text here, plain text, and this happen, entire thing is happening, and then you get the output, and this is the kind of power trace you get for one such encryption. And you can actually see there are some specific pattern, right. So, you can see here that you have this kind of pattern, right. So, you can see that there is a fixed kind of pattern here, the same thing is happening like this, right. You can easily make out that this is basically nothing but your round 1, this is round 2 and so on. So, you will see that there will be 3 rounds, 10 rounds here, right. So, you will identify this is basically the power pattern corresponding to one round it will, right. So, probably I do not need to check for all rounds, I will focus only on one round, right. So, because when the same kind of operation is happening, and I will specifically be interested to in round 1, because that is where my the text is more closer to what I am sending, right. The cipher text here is just XOR with the add round key, right. So, usually the mount the attack happen in the round 1, right. So, where I do not need to look for the other rounds. Okay. So, I will basically focus on the power consumption in this. So, let us zoom this, what is when if you try to extend this, what is happening, let us see. So, this is the kind of the power traces for the one round or the round 1, right. And what are the operation is happening here is basically S box, then shift row, mixed column and add round key. So, in a careful motivation observation, because you have to do things multiple times to identify what is your point of interest, you will see that there is a kind of spike here, right, and you can correlate that this is basically nothing but the S box operation. So, this is where the S box operation is happening, and there is more power consumption is happening here. So, that will be my kind of point of interest, right. So, I will try to look into the S box operation and the power consumption corresponding to the S box operation. Okay. And you can this is basically you have to do it for multiple such traces to look at whether this is consistent or not. It is just basically for one trace or one text, or it is happening for all, right. Then we will basically see that it is basically happening for kind of all. So, this will be my point of interest, right. So, this is basically where I try to look that, okay. So, I will take the entire AES, I will only look for round 1, and within the round 1 I will look for only the S box operation, clear. So, now what I will do? So, now I will run many encryption, okay, and I will try to put this in a frequency domain, frequency distribution. So, it is basically you can see that this x axis is basically the power value, right, whatever the power consumption. So, now what I am doing here is that how many for text sites say probably run for 10,000 or 20,000 plain text, okay, and I will measure that for how many such plain text the value of this power is 120. So, I found that almost 15,000 for text the value is kind of 120. So, this is the kind of number you say that there are hardly for anybody is 0, right. So, you have basically very few your power consumption is 100, for very few 100 power consumption is also 140. So, this is the kind of frequency distribution that this many traces the power consumption is this. So, this I can plot, right, just run this and I get the power and I just put it and I will get this value, right. So, this I will do, it is possible to do, right. Now, I have to find the selection function. How do I basically distinguish between something, right. So, what is happening here? So, you have the plain text and in this and that which is basically XORed with the key in this add round key, and this is your ciphertext, right. So, if I have this ciphertext, if I have this particular, say I will just pick one of the bits of that, it is basically 8 bit, right. Let us say I take one bit of them, and I will see is if I make this particular. So, I will run now again for 10,000 or 20,000 plain text, but I will make that, so let us say the LSB of that bit, right. So, I will just make that LSB equal to 1 or LSB equal to 0, right. So, rest of the bit can be arbitrary. So, you have 8 bit, so you have basically 128 bit, but I will just only make the last bit 0 or 1, I make 2 distribution, right. So, I have and then I run it. So, maybe for say 10,000 test cases, and is there a difference in the power pattern, and I found that yes. So, whenever it is 1, the power pattern is this. So, the number, so basically the maximum power is coming for say here, so this is basically the maximum is coming here when the power may be say 115 or something, but here it is coming here, right. So, there is a completely different power pattern, it is well distinguishable, understood. So, it is basically, you remember I have 2 set of plain text on which I am running, in which my LSB is 1 and the and another case its LSB is 0, rest of the bit is random. So, now from this power pattern, now if I see this difference, then I can actually get I can distinguish between these 2 power, right. So, this is basically my selection values, right. I will see how I am going to use this to do the actual attack. So far it is clear what is happening, right. Okay. So, I identify this bit which basically will make the distinguish, I will make the LSB as my selection bit. And if you put it in the frequency domain, you will see that the difference, there is a significant difference where this bit is 1 or 0, right. This is corresponding to the bit 1, this is corresponding to bit 0, the LSB, and I am seeing that there is a difference, this is the difference, okay. And there are significant difference, and that is why this was coming, right. The distribution is not same. Get the point? Yes. So, this will help me to identify the key. So, I have done my homework, I do some experiment, I figure it out which bit to track, which operation to track, and how to track. So, everything is done, now I have to do the actual attack. Okay. So, so now basically I have already done this find the points of interest in my design. I will now do this, execute the algorithm and collect the trace. So, that is something is I am going to do, and let us see what I am going to do. So, this is that same AES algorithm I have already talked about. I will now show you basically what is happening in this algorithm with animations. So, your plain text is say 128 bit, and then I will or sorry, this is say 16 byte, okay, which I will put it is 4 cross 4 matrix, right. So, each of them is basically 8 bit, right, which is basically this value is there. So, I am basically make it matrix, right. This will be my row 1, this will be my row 2, right. So, this will be my row 2, this will be my row 3, and this will be my row 4, right. So, this is how I just encapsulate this text into a kind of 4 cross 4 matrix, right. So, each of them is 8 bit, and you also have the A key is also 128 bit. So, that also I can put as a this matrix, right, because there are 16 location into 8, which is 128 bits, right. So, I will basically distribute my key into this is how the AES is being implemented, right. So, this is also for kind of 4 cross 4, and this add round key is doing nothing but XOR, right. This is XOR. So, this is my ciphertext or this actual plain text that I am giving, and I just XOR with the key. This is secret to me, and I get this matrix where it is basically XOR of this bitwise, this location wise XOR, right. This and this I will do XOR, I will get this value, right. This and this I will do XOR, and this will come here and so on. This is how the XOR is happening. Okay. So, then you have this S box where we are going to mount the attack. So, this S box is what? So, you have this ciphertext which is kind of 4 cross 4 matrix, right. I will, and you can think about this is 16. So, I will just pick this, I will and this is basically so this is my actual input, right, xin, which is basically this is my x, right. So I'll basically pick one of this location value, which is basically say suppose this or this, and I'll XOR with this kn, which is the add round key, and this value will be the index of this S box, right. This is my S box, right. So it's basically you identify, this will become the index and you get that value, whatever the value is, it's a predefined, everybody knows that, and that value will replace. So suppose I take 9, I will go to the location 9. So suppose this is 0, 1, 2 and so on. So suppose this is your 9th location. So I'll do say this XOR key, say this give me say 5. So I'll go to the 5th location, whatever the value, I'll replace this into this, right. So I'll replace here 3. So this is S box, right. So you basically take the plain text, XOR with the key, whatever the value, that will be the index of this S box, and from there you pick the value and put it here. Okay, this is S box. And this shift row is the next operation. So this is substituted by our S box. Shift row is basically you shift the first row by nothing, right, second row by 1 bit. So the basically this will come here, this will come here, this will come here, and this will go back to here. So it's basically shift by one location, this is shift by 2 location and so on, right. And mixed column is basically you take this column and multiply with this column, right, and then you store back into the ciphertext. Okay, this is the operation. Okay. So, but we are interested more on this, right, because this is where I found the difference in this sub byte operation. This is what I already talked about. So I have already identified. So what I am going to do now? So yeah, so the same thing is explained here again. So you have this xn is the plain text, which is the known to you, right. This is unknown or secret, and this is also unknown. Unknown because you cannot access this value, this is some internal values, right, you cannot access it, but I can control this, right, and I am objective to get the secret. So what I'll do, I'll basically effectively doing this SI operation, right, you are accessing the index, right. This is what I basically say, this is known variable, this is secret, and this is unknown. So now I try to develop this algorithm, right. Can I have some tester which can identify the key, right. So if you go back here, I know this, I do not know this, and I have no access to this, and I try to guess this value, right. Can I have a tester where I give this different value of this, and I want to measure the power, not this one, and I can guess each kn in my key, that is giving the desired power, right. So this is the kind of tester. Understood? So this kind of algorithm I need to develop, right. So I need to develop this particular algorithm. Can just I give some one key and I will do this power analysis and tell me whether this key is the correct key or not, right. And you remember, I just tell that if this is the correct key, what will happen? If you give that LSB 0 and LSB 1, that should give you 2 different power pattern, right. So that is the kind of differentiator. So so your key value, if it can give you that differentiator, then I can say that this is the correct key, right. So how many combination you will have? You remember that if you go back here, so this is your key. So you have basically 16 location, but I can do independently, right. Each of them is 8 bit. So this is 8 bits and there are 16, right. So effectively for that 8 bits, there can be 256 combination, right, 2 to the power 8. I will at most to identify this key, I have to try 256 values, right, and I have to try such 16 times, then I will get the entire key, right. So this is the idea. So effectively you have to do the entire thing for at most kind of 4096 times to get the entire key, right. So this is what basically been done. So what I am going to do now, this is now kind of understood to you that I know this, I have control to this value. So, I will basically give say 10,000 or 1,000 such plain text, and I will pick a specific value to this, right. So, I will set it to say 0, then I just assume whether the key is 1, key is 2, key is 3 and so on, and then I will do this, I will access this and I will get this, but only thing is that this is not available to me, but I have the power pattern corresponding to this, right. So, what I will do, I will take this value x1, x2, x3, x4 random values, and I will take a specific value, right, a specific value, and then I will get 2, and then in this I will distribute this value into 2 set for 0, this is for 0, for LSB equal to 0, for LSB equal to 1, and then I will see whether I can distinguish between them or not, right. So, if I can distinguish, then this is the key, right, that is the idea, get the point, right. So, this is exactly I am going to do, that I will basically run it, I make sure that I will just point on the LSB, I will distribute them into 2, whether it is 0 or 1, I will get 2 power pattern, and I will see whether the actual thing that I have identified earlier, that actually following or not. So, if I can see that this is for 0, this is for 1, say LSB equal to 0 or 1, if they are distinguishable, then this is the key, if it is not, try the next value, and at most I have to try 256 times to get the key, right. This is the idea effectively, right. So, if I get this, then this is the key, otherwise you go to the next one, right. So, basically the same thing. So, the tester will work like this, understood. So, this is how effectively you can crack AES algorithm. It has been shown that it can be done in minutes nowadays, maybe within say few minutes you can actually given an implementation. I think Professor Mishra's lab have this facility and they can easily identify the keys for AES if it is running on FPG or anywhere, and this is the kind of overall idea. Okay. Any question here? Everybody understand this, right, the core idea?
Sir.
Yes.
So, DPS stands for, here is the P stands for plain text or power?
Power. I think differential power attack.
Power
Yeah.
attack.
Yeah. Yes.
One question that this has to be an intrusive method.
Sorry.
This has to be an intrusive method. Can it be non-intrusive?
What do you mean by non-intuitive?
As in, sir, that I do not need to open the box itself, and such as we do the EM one, in that from far off we can do it. So, is it possible to do it, or
So,
do I have to
here
open
you
the box?
somehow access the power when you are running the text on the device.
Sir.
You are in the physical proximity of the device and you are able to measure the power.
Right. Sir.
Okay. So, if you can measure, you will get the entire trace, you will not get the only that part, right, but you entire trace you only consider that part which is interesting to you, right, and then you do the analysis. Yeah. So, that is the kind of, but it is possible in specifically for say edge devices, IoT devices, right, you can always attacker by another and they can get the key, right.
Right. Sir.
Okay. So, this is the idea effectively. So, say for example, you are running for k equal to 101, k equal to 102, and then you found that, so that is not differentiating, but whenever you are running for 103, you see the differentiation between the LSB and MSB. So, LSB equal to 0 and LSB equal to 1, and say then you say this is my key, right, not the others, and I will stop there. Whenever I get it, I will stop there. Okay. So, this is basically the first part of my talk, that how effective this power analysis kind of attack, power side channel attack happen. Okay. Yes, please use the mic.
Sir, how can we say that by making the LSB equal to 0 or 1, how we can test the keys?
So yeah, it's a good question. So, basically your LSB may not able to distinguish, right. So, then you have to take the next bit and all, right. So, effectively what you do, you make the LSB equal to 0 and other bit is arbitrary, you run for 10,000 cases and you plot the pattern, and then you make it 1 and rest the bit again random, and again pattern, you make the pattern, this plot the power pattern, and if they are distinguishable, that means this is actually distinguishing, right, it actually have an impact on the overall power. So, but your luck may not be that good that in one chance LSB is differentiating, it may be the other bits, right. So, and Identifying the S box also will take time, that you have to mount the attack on the S box, not on a round key or mixed column, right. So, all those things you have to do, but I think for this kind of AES and all, these are all well known now. People only attack on the round one and S box operation, and just LSB is the differentiator kind of. Okay. For new say encryption, you have to spend some time to identify that thing. Once you have done that, you have to do just this step to get that. Okay. Okay, thank you. So, this first part is done. Now, I will move to the next part. So, in this talk, I am going to talk about how do you protect it. So, it does not mean that that AES is now useless, right, it is still used everywhere, right. So, how do you basically make sure that you still run the AES and people can access the power, but they cannot get the key, right. So, that is the challenge, right. So, you basically make some modification to your AES algorithm, so that the power does not depend on the key. So, its basic idea is that you have to randomize the power, the dependence between power with key, you have to break that chain, right. So, if you can do that, power is independent of the key, then you will from the power you will not get it, right. So, that is the kind of key idea, that you basically make sure that your power is not proportional to or specific to the key, right. So, you randomize this. So, and it is exactly being done, that you introduce some random number in your computation, right. So, that each operation is now randomized with the random numbers, so that your correlation with the power consumption and the key is broken. That is the overall key idea. Okay. And the technique called masking, it is a very well researched area. There are so much of work has been done, it can take maybe many hours to explain all the masking techniques. So, what I am going to do is, I will tell you what is the concept of masking, and if you want to mask an AES algorithm, specifically the S box, because S box is the weak point, what are the things you should do, and then if you try to implement in software, what kind of changes to needed, and if you bring into hardware, which is our of interest, what are the things you will do, right. So, these are the things I am going to cover. The core concept of masking is software version as well as the hardware version, right. So, what are the things you need to take care, so that the masked implementation power side channel is not possible. Yes, please.
Sir, by doing masking, will it increase the resource power consumption for the system?
Exactly. So,
like we have constant IoT devices where resource, they are constant resources. So,
it is a very good question. Masking has huge overhead. Okay. I will show you today that masking on AES can have 27x area overhead. So, original masking AES may be say 100, it will become 2700. So, this much overhead is there, but in certain secure application, people do not care about the overhead, they want a secure version. So, then they do not bother, they want the highest level of security, right. And then in the second half of the talk, after break, I will talk about what are the low overhead implementation, right. So, how do you protect your design with low overhead. Okay. So, it is a very good important question, that masking has security guarantee, but comes with lot of power as well as area. How do you basically balance between, say probably I do not need to protect it completely, right. So, if you make sure that people cannot break within 1 million of traces, so we are just talking about 10,000, 12,000, right. So, if you say that if you take 1 million traces, still you cannot break it, it is kind of safe, right. People do not have that much of energy to go beyond that, right. So, there is kind of a trade off between the security level versus the area overhead, and you should specifically for IoT devices and all, you should have a trade off between this, right. So, in one of my talk, I will go talk about that, what is the trade off and how do you basically get a good protection with less overhead, comparatively less overhead, that I will talk about. So, what is the core concept of masking? It is basically, think about that you have one x, right. So, x is your secret. So, whenever you do say x or y and the output z, so some information goes here, right. So, you basically the correlation of x comes here, right. So, what I want to do, I want to break this x into shares. Okay. What I am going to do, let us say I want to make 2 shares. Okay. So, what I will do? I will take one random variable r and I will do x XOR r, that will become my share 0 or x 0 and r is my share 1. I have now 2 shares. Okay. The bottom line here is that if you somebody have access to both the share, he will get x, right, because if you have this XOR r, it will become x. So, how many shares you need effectively? Based on the assumption how many value you can trap in your design. If you say that I can have only one point I can access in the design, then 2 share is fine, because you will never get 2 value from one point, right, you will get only one value, right. So, if you basically have access to one point, I will make 2 shares, right. If I have 2 access, I will make 3 shares. So, that with 2 access you will not ever get x, right. So, here the idea is that if you have access to both shares, you will get x. So, if I have say 2, I have to make it 3 shares, what I will do? I will do x XOR r1, this is my share 1, and then I will have r1 and then r1 XOR r2. So, I will just bring 2 random, right, and if you do XOR with all these 3, you will get x, right. So, but if you get only access to say 2 values, say basically this is for 3 share, right, this is I make it r2, this will be r2. So, if you have say, that is why I told you that this is 3 shares, right, original value is x, I introduce 2 random variable r1 and r2, I will create x XOR r1, that will be my input to the device now, r2 and r1 XOR r2. So, there are 3 value is the input to the design, and if you have access only to say these 2 value, this and this, if you do XOR you will get this, this is not x, right. If you have access to say this and this, if you do XOR of this you will get this, but not x. Similarly, if you have access to this and this, you will get only r1, not x, but if you have access to all 3 variables, if you XOR you will get x, right. So, based on your assumption that how many access point an attacker have, you decide how many shares you want to create for each variable. Understood? Share part is done, right. So, what else you have to do? Once you create the shares, what else you have to do now in your implementation? You have the AES implementation, right, add round key, mix column and all. What I have to do? I have to rewrite those operations in terms of now this, because I do not have x anymore, right. I have now this is share 1, this is say x 0, x 1 and x 2. Now, I have to rewrite my entire function in terms of x 0, x 1 and x 2, because I do not have x anymore, right. So, if I want to implement this in software, you have to rewrite the entire thing in terms of x 0, x 1 and x 2. I will show you with examples. Okay. So, this is the same point, and this is basically an arithmetic masking. So, before going to that, this is Boolean masking, because I am assuming values are Boolean single bit, but if you have say multiple bits, the shares I will create. So, if I want to create 3 shares, this will be my share 0, this will be my share 1 and this is share 2. So, it is basically x minus r1 minus r2, x is my secret, right, x is the secret, and this may be 8 bit, it is not Boolean value anymore, right. And then I will create x minus r1 minus r2 and mod p is just to keep the value within p, right, 0 to p minus 1. And the next one is r1 and r2. Again, if you will see that if you do you have only two value access, any 2 of them you will not get x, but if you have 3 of them you will get x. You can see that r1 crosses with this and r2 this, you will get x, right. So, this is how you, if you have your circuit is in arithmetic level, you implement this, or if you want to have a Boolean circuit, you implement this. So, this much is done, right. So, people have you do this regularly. So, then what you have to do? In software masking, you have to rewrite everything in terms of x0, x1 those shares, right. So, to give an example, suppose you have an AND operation which is A B AND of A and B. So, this was the operation in some say in original original equation, right. Now, I break this A into two shares A0 and A1. So, where A0 is A XOR R1 and A1 is R1, B0 is again the same way, that B XOR some R2 and B1 is R2, and C0 is C1 similar way, right. There will be two output now instead of one output, because I have two shares, it is kind of a duplicating your circuit, right. You have to do everything on share A0. Earlier you have some computation AB, right. Now, I have to do AND operation on A0, I have to do some AND operation on A1, B0, B1, right, something like this. So, the so what I will do, I will basically rewrite my operation like this. Okay. So, you do not need to go into all detail, effectively now one AND gate will become this. Okay. So, you have basically earlier A, B and C, now I have this is my AND operation, because I have share A0, B0, A0, B1, A1, B0, A1, B1, right. These are the 4 shares. So, through now AND will be implemented as this, and there are this Z is another random, I will talk about bit late about this and another say 5 minutes why this Z is also needed. This is another random, okay, and this is your Y0 and Y1, and if you do XOR Y0 XOR Y1, you will get the Y, what was the actual output or C, right. So, it is basically C, the actual output. Okay. So, or say I would say this is C0, right. So, in my as per calculation this is C0, this is C1, and if you do C0 XOR C1, you will get C, the actual value that was computing earlier. So, now I think it answers your question now, that how much overhead we have, right. Just one AND gate is becoming 4 AND gates plus 4 XOR gate, right. So, one gate become 8 gates, right. Earlier delay was 1, now the delay is 3, right. So, your delay will increase, your area will increase, but here nobody can get any information about A and B, because it is all things are random, right. Your A0, B0 all are random. So, there is no correlation with your secret A and B with the power consumption. So, I can guarantee that power side channel is not possible, but this is how the things will be done. Okay. So, I will now move on. So, I will now see if I have some implementation in C code, say in software level, what are the changes to be done. So, I am taking this can write S box implementation, because I want to bring this into hardware, right. So, the S box also it looks like good that you basically do S of I, right. This I is basically X I N XOR key, right. This is what you do effectively K I. But what is the size of this S box? So, this basically 8 bit, right. So, that means you can have 256 location, because 2 to the power 8. So, the S has 256 locations 0, 1, 0, 1 to 255, and each of them is basically 8 bit, right. So, it is basically 2 to the power 8, 8 into 2 to the power 8, which is basically 2 to the power 16, it is lot of area, right. So, in hardware what people do, you want to access this, but I can rewrite that in terms of function, right. So, what I will do is basically what this S box, you can think about that this is equal to y, right, you are doing this. So, what I can do, I can write all possible value of this SI, that if I equal to say this is 8 bit, right, say 0 0 0 0 0, the output is whatever the S box value S0's value that will come, right. So, this is 1 0 1 0 something like this. So, this way if it is the value is 1, what is the value? This way I can think about what if this is 255, what is the value, right. So, now this is my Y0, Y1, Y2 and so on, and I can just like your Carnot map minimization, I can identify what is the Y0 value, what is the Y0 in terms of this X0, X1 to X7, and what is Y1. So, I am just giving you the idea that although it is a fixed value, but I can represent this as a function, that y 0 is a function of this, y is a function of this, and then I do not need the memory. Understood? So, this is what basically logically being done. Everyone understand this concept, that I do not need to make this 2 to the power 16 memory. Instead, I make this access Si equal to y. I know the values of this basically 0 to 255, this is also 0 to 55. I make this table and I identify what is the relation between y 0 to this, right. This is what you do in your Carnot map minimization. So, once you do the hardware, nobody does this Si equal to this. So, what they do, they basically write as a function, but it is not exactly the thing I am talking about here. They make more sophisticated implementation, so that area over it is much lesser. Okay. So, I will basically in high level I will talk about later. So, one of the function when you implement this in the for hardware, this S box using Canwright's idea, one of the function is basically G56 inverse. I will talk about that more detail. So, this is the kind of C code corresponding to the original implementation. Now, I want to mask it, right, and this within that you have this G16, which is another function which is calling again G. There are 4 functions. There are G4 SCL, which is multiply with constant, G4 multiplier, G4 square. This will again call G2 this, and that will call a AND operation. Okay. So, this is the kind of call graph. Okay. This I will talk about what is this inverse function in a moment, right. I just give you the key idea, but the same I will see the exact implementation. So, this is your C code, you understand, right. This has this many calls, there are G16, there are 4 5 function call, each of them has a body that will call another function that will call the AND operation. Okay. So, this is the implementation. Now, if you want to mask it, what I am going to do, I now say suppose I have 2 shares, each variable becoming 2 shares. So, earlier you have this A, this will become A0 and A1, right. Suppose you have the input was x, that become x0 and x1. So, this x0 again x XOR R1 and x1 is R1, that I have already talked about. So, instead of giving x, I will now give this x0 and XOR, I will do the XOR and I will give that as input. And each operation, wherever I was calling say G4 mul AB, this will become now 2 function, right. So, you basically have so AB was yeah. So, let us say when this one, if I take this one, so you have this one. So, now instead of sending EB, I will send E0 E1, B0 B1, right, and output is was P. Now, I have 2 values, right, P0 and P1, 2 shares will come. So, effectively you have basically everything become double, right. If you have 2 arguments, that will become 4 arguments and so on. Everybody understand the core idea, right. So, for example, if you have this say A, now you calculate A00 and A001, right. So, you will have 2 value will calculate. Okay. So, so this is what I was talking about, that this will call this function and finally, it will call the AND operation, and this is that circuit I talked about, the implementation of AND gate, it is called DOM AND. Okay. I will talk about that in more detail. So, and then finally, why I have introduced that one more random, because this is called non-linear gates, and non-linear gates actually need more protection. So, they add one more random here. Okay. So, no need to go in that detail in this course, but that is the idea. So, basically if I have give you this code, I can write a tool or software that can give me this code, right. So, this is the kind of masked version of the AES, and if you run it, you do not give any power, it is not possible to do the power side channel attack. Okay. So, this was the kind of the theory, the D probing model that I talked about, that you have at most D locations of the circuit is available to you, and if you have D plus 1 shares, that is safe, right. So, if you have D probing model, you make sure that you have D plus 1 share at least. Okay. And perfect matching says that that is the theoretical guarantee that any D locations, right. So, it is basically if you have the system has n location, it is kind of NCD, right. You take any possible of D from that, and that also give you give you the leak, right. So, that is the kind of theoretical guarantee, and because of that so much of overhead, right. Ideally you cannot take all possible combination, right, but theoretically you have to prove that all possible combination of D values inside values from n locations won't give you the delay, right. So, they mathematically prove those things, and I am not going to detail, and this is the kind of history. I am not again going into detail, and this is the theory. So, now I will talk about the hardware implementation. So, software part everybody understood what I did. It is basically you break into shares and rewrite your entire thing in terms of shares. Core concept is understood, right. So, no need to go into the each line of the code, understood. So, as I mentioned that this S box operations is the kind of things where you need the more protection, and then I do not want to implement that as a array, because memory it will take lot of memory. So, what they does effectively, they use some inverse affine transformation followed by a inverse table and then another affine transformation. Again I will try to not want to go into that detail what is that, but I will now try to correlate with this versus the code I have shown you earlier, right. So, what is this affine transformation is basically this A x plus c, right. This is basically is happening here, is basically A x plus c, nothing else. And why they do this, let us skip that. And then you have the inverse table. So, again you need a table. So, they do not want that table. So, they will replace that with again that some operation. So, I do not want to this table, instead I want to do using computation, and this is the kind of computation. They break that into this and lot of equations, but finally they compute that table value using some equations. The core idea I have already shown you, right. So, finally this is your S box implementation, right. It has basically one square multiplier, this is sorry square, this is multiplication and constant multiplication, right, and then inverse GF. So, this is what I was talking about. So, what this so if you remember that I was showing this code, right. So, now you see that this square constant square multiplier inverse, this is basically these boxes, right. So, effectively this is why I show you this code, right. So, this is the kind of hardware targeted AES implementation. So, every box will see a, so this is the multiplier, right, this is the square function, this is multiply with constant, this is multiply with constant, this is square and so on. Okay. So, this is one part. So, once you try to implement in hardware, you need to replace that memory with computation, and this is the kind of things we will do. Okay. The next important point is the glitch. In the hardware, you know glitch, what is glitch? Everybody knows it? It is basically if you have two, say suppose there is an AND gate here, right. So, two values are coming. Ideally, if it is say 1 and 1, the value should be value should be 1, right. That, but say that this path is longer than this. So, this one come little bit late. So, for a moment of time there will be 0, right. This is basically there will be a moment of time there will be 0 and then there will be 1, right. So, this is glitch. So, whenever you have a circuit, not all paths are properly balanced, and there is a basically the delay of both the path is not same. So, the value will not reach at the same time, and there will be very fraction of time within the clock there will be a opposite value. What was the expected value? You will get the opposite value, and that called glitch. And in hardware, this glitch actually consume more power. So, you should try to develop circuit which has less glitch. Glitch consume dynamic powers. Okay. So, that is one side of the story. But people have shown that this glitch actually give more option for the attacker to get the key values. Okay. So, glitch actually also not safe in terms of power side channel attack. So, this glitch analysis people can identify the key, and I have one example for you. So, suppose you have some implementation where these are the shares, right, x1 and x2 is the share of one variable x, and y1 and y2 is the another share corresponding to y, and say this is the computation is happening. Now, let us say this x2 is glitchy, okay. This x2 is glitchy, that this x is coming little bit late compared to y1 and others. Okay. And if you do a thorough analysis, that they can identify that before the glitch. So, if the value of y was actually 0, the before the before glitch, the how many times your and this AND operation is happening here, right. So, this if you just probe here, how many times your value was 0 earlier and then what is the next value. You can see that only 2 occasions the value changes, right, sorry, up to this. you make a line here. So, in this part this the before plus is the value just before glitch and this is the after the glitch. So, before glitch it was 0 and then only 2 cases it is 2, right, and whenever y is 1 you see the numbers 1, 2, 4 cases it is non-zero, right. So, if you just notice the value at this point before glitch and after glitch, you can clearly say that value of y is actually 1, right. If you, the number of time, just counting the number of time the value changes before glitch and after glitch, right. So, this is basically again problematic, right. So, glitch actually can create problem and actually can give more option for the attacker to attack your circuit. Okay. So, you need to protect glitch. How do you protect the glitch? It is basically I say that there is something like this, it will basically propagate through your circuit, right. The idea is that wherever the location of the glitch, if you put a register, the glitch stops there because values become stable there, right. So, basic idea is that if you have normal model, if you have access to this point, you cannot guess about this, but if you have glitch, if you have access only to this, you can actually reason about this as well as the reason about this, that I have shown you what example, right. So, the protection is basically very simple, you need to put register, right. So, you have to put register. So, if you say that there is a possibility of glitch here, you put a register here. Okay. So, that is the solution. So, you need to put some register in your design to stop glitch propagation, and if you do that, that will give you the protected circuit. So, this is why this in the DOM you have this register you have to put after this cross domain computation. So, that is basically that gadget, it talks about the gadget. So, you how to basically as I mentioned that AND is nonlinear operation, you need more protection, and I have shown you that one case, right, that you have to move one more random here, and they say that you put another whenever you are cross domain computation. So, this is from the same domain, right, 0 is one domain and 1 is one domain. So, this is same domain, this is cross domain, this is cross domain, sorry, this is same domain, this is cross domain, because B0 A1, this is B1 A0. So, whenever there is a cross domain computation, add a random and put a register, okay, for more protection. This is theory, again why we can then there will be no leakage. Okay. And this is the final implementation of AES with DOM, and this is very low overhead, you can actually see the overhead, this is very low overhead implementation. Okay. And just before conclude, I will talk about the gadget, is basically how do you implement the AND gate. I talked about this, which is basically DOM, right. So, you have basically A0 B1 and then you have A0 B1 and then this random, you put a register here and you get 2 output, and if you do XOR of them, you will get the actual output C, right. But there are many other gadget possible and both have security guarantee and different. So, in literature you have HPC 2, HPC 3, then HPC 1 also is there. So, there are many gadget, and again I do not need to go into detail of them, but you can see that their area is different, number of register is different, latency is different. So, based on your, but the more area and more registers, the protection is more, right. So, based on your security requirement, you can pick the gadget what you need. Right. It is basically how do you replace the AND gate, you can replace by this or this. Okay. You can see here it has latency only one level, right, and one random. Here you have so many registers, but how many latency, this is one level of latency, this is another level of latency, this is another level of latency, right. So, 3 level of latency added plus so many registers, right. Here you have 2 level of latency, but register is also less, but I think there will be more random here, right. So, it is basically it has only one random, it has 2 randoms, right. So, there are 2 randoms. So, it is basically this is another direction. If you use more random generation also is costly, right. How do you generate the pure random number? So, some people want to use minimum random, but whenever you use less random, your number of register and latency will increase. So, it is a trade off again between the number of random you want to use versus number of latency you want to use in your design. Okay. So, that is a cryptographic designer job, not our job, but the core idea is this. Okay. So, that is all for now. We will have break for 30 minutes and we will come back. Then I will talk about how do you automate this process, right. So, if I give a normal AES code, how do you give me this Verilog code corresponding to this? Is it possible to generate? And if it is, then what are the things to be done and how do you get a Verilog code automatically from a AES implemented C code. So, that we will do after half an hour. Okay, thank you. I think tea is outside, right? So, you can have yourself. PDF के ऊपर नहीं लिख सकते क्या? PDF I cannot write. This slide is in PDF. थोड़ा होने से ऐसा नहीं हो रहा है, मुश्किल है. बट आप लोगों का होता कि नहीं है? मेरा जो नेक्स्ट अपकमिंग कोर्स है उसमें पूरा ही PDF है, एंटायर स्लाइड सब. मतलब मेरा एक और एक Okay, so welcome back. We'll start. I think we are not getting any question from online participants, so please feel free to interrupt us as well. Okay, so in this particular class, what I will talk about how do you implement power side chain secure hardware. So that is the kind of objective. We have already talked about the masking. Effectively, you have to mask your design, right? So that's bottom line. But will you write your Verilog code directly, or I will write in C, and somebody can convert that into me in Verilog, right? So that will be easier, right? So whenever you write something in abstract level, that will take less time, right? So the idea here is that if you have your design in C or C++ and I use certain softwares to convert them into hardware, and I guarantee that the design is side chain secure. So that would be the best thing, right? Your involvement will be minimum. Okay. So this is one such tool which is called masked HLS, which is we develop, which effectively can do that, exactly that what we are talking about. The high level synthesis, HLS stands for high level synthesis. High level synthesis is not something a new concept, it is 30 years, 40 years old concept. It is basically a software which takes C++ program and give you Verilog, and it is a very good or a well used tool. And in the second half, I will talk about if you have a ML model, trained model in Keras or Python, how can you utilize this high level synthesis tool to generate hardware. So that part I will talk about in the second half. But what we have studied that these high level synthesis tools are very sophisticated. Okay. This tool can do lot of optimizations. It can actually pipeline your design automatically, it can do data flow, it can do unrolling, many things this high level synthesis tool, the commercial versions can do, which is good. They have developed that to make your design efficient. Okay. In one lecture, in the next lecture, I will show you how can you utilize those features to make your ML accelerator very efficient. Okay. But we have experimented here that those features of high level synthesis is counterproductive when you try to develop masked hardware or a secure hardware, because those optimization never see what is your security guarantee. They just optimize in terms of number of area or say number of latency. So, overall latency or area. So, what we have experimented and figured it out that if we use the commercial high level synthesis tool from various industry like say Xilinx have Vivado HLS, Mentor has Catapult, many other high level synthesis tools are available, even open source tools are also available. So, they actually interfere in the security guarantee that they are in the C code, right. So, the C code, by C code what I mean, that masked version whatever I talked in the previous class, right. You have the original C code and I convert into masked version, which is very straightforward job. But once you give that straightforward this particular masked version, you need the operation exactly in that way. You need a register in a specific locations and all, but HLS does not guarantee that. It optimizes further, and we have seen that as a result, although your C code was protected, but once you generate the Verilog, it is not protected. It actually interfere the protection, the security protections in the that AES implementation, and that is the most important thing, right. We have to make sure that your generated Verilog code or the hardware is secure. It may use 10% extra area is fine, but I cannot touch that part. So, what we kind of concluded from the study that the HLS tool that is available, they are not good enough to do security aware synthesis. Okay. So, that is why we come up with this tool called masked HLS, which we have shown that we will show that whatever optimization they do, the normal HLS tool, they are not that useful, rather you have other scope of optimization that those tool does not do. So, the optimization objective inside this masked cryptographic design is something different from the normal optimization. The exactly what was sir was saying in the previous class, that the general purpose processor, to make it running for this machine learning models and all, it is not a good idea, right. You develop GPU, a specific architecture corresponding to which actually can take care of those. The same concept here is there. You do not do all the optimization that is needed to make your generic circuit optimal, rather you identify what optimization you need and do those only those optimizations, and that will make sure that you get an efficient hardware. Okay. So, that is the study. So, I will talk about that in detail in this. Okay. So, I will have little bit of overlapping this masking gadgets and all that I will just quickly go through, but this part will be discussed in detail, right. This is the kind of the things that we have discussed mostly in the first half of this class. This setup everybody understand that power side analytics is possible and it can be done in minutes. So, the challenge is basically how do you prepare that hardware, and as I mentioned that first of all you need the masking countermeasures, and then you need also to do something, you have to protect against glitches, right. You have to add register certain places. This masking I have already discussed that you break things into shares. If you have a variable x which will be splitted into d plus 1 shares, and you cannot, the idea is that you should not combine more than d shares. If you will get the original value and you combine all the d plus 1 shares, right. So, it is basically deprobing security. You make sure that you do not have the facility to access d plus locations of your design, right. So, this is understood, and this is again the same thing, you can only get by combining all of the shares, not part of that. Okay. And as I mentioned, the nonlinear operation like AND operation need special care, you need further randomization, and also for masking you need a register there, right. So, that is the things, a recap of what we have discussed in the last 1 hour. So, the idea is that you have a software mask code, you have the original code, you basically replace everything in mask this shares, then you replace all the AND gate with this nonlinear gadgets, then you get that version of C code that I have shown you in the previous class, right. And then for hardware, as I mentioned, you need to add registers to stop glitches. The question what we are asked, can we do this transition through high level synthesis, right, can I do it automatically, and you generate the Verilog. So, this is the same AES can write S box I talked about, that you have a G256 inverse agar, and then you have inside that it has G16 and it is calling G4 which is calling G2, and that will call DOM AND, right. So, that is the kind of recapping the same thing again. When you have this unshared S box, you have these are the call graph, and then you replace all of this variable with the shares, right. A will be replaced by A0 B0, B will be replaced by A1 B1 and so on, right. So, effectively the call graph, the parameter will change, right, and so that is the kind of call graph. And then this was I have shown earlier that if you have a G256, this is the call, this will become this, right. This I have also shown that this all this variable will be shared, and this is the shared version. And then within that you basically have this G2 call, which is replaced by the DOM AND, right, and the DOM AND C code is look like this, that graph I have shown you, right. So, so effectively if you now do the inline, this will be looking your C code. So, from this code, which is that maybe 6-7 line, which after conversion of everything into share version, replacing that DOM version, the AND gate with this code, and then you inline, you will get this kind of C program, right. So, this is straightforward task. Anybody who know how to write, how to handle parser level, I mean parse the C code and modify this, he can do that, right. It is automated in our flow as well. So, you will give me effectively this code, you will give me this code, I will give you this version of the code, right. So, it is basically automated. Any questions so far? So, this is very important to understand. So far we have discussed this, you should able to tell yes, right. Anybody who do not understand this flow, this conversion, and why I am doing this? Yes, or should I put more effort on explaining this? Anybody? Understood everyone? Please. Yeah. Any question? Can I repeat? Yeah. So, if you remember the masking, you know on masking, right. So, masking is effectively you replace your actual secret value with shares, and then you have to rewrite the entire computation in terms of shares. So, for example, earlier you have a variable A, now it become A0 and A1. So, you have to now rewrite everything in terms of A0, A1, right. So, that is what I am doing here. So, instead earlier you have a X here, it is now input is X0 and X1. So, there is no X anymore. So, wherever X being used, I have to use X0, and I have to create 2 copy effectively, right. I am using X0 here, X1 here, right. So, effectively this something I have to rewrite entire thing in terms of the shares, that now understood. So, this is I have to replace everything. So, for example, you have a earlier you are sending, so you are calculating earlier A, B, C. Now, what is happening here? Now, A0, A1, B0, B1 and C0, C1 somewhere. Okay. So, instead of calculating AB, you are now calculating A0, B0, A0, A1, B0, B1, right. So, wherever you are using A, I have to now send both A0, A1, right, that is the idea. So, this is in terms of rewriting everything in terms of shares, understood. And as I mentioned, finally, wherever this AND operation, that will be replaced by the gadget. Gadget I have already discussed, right, DOM AND and all, and the gadget code is like this. This is basically that graph I have shown. So, now if you replace everything, your this version of this code will become this, right, after inline, understood. Any other questions here? Yes, please.
Sir, what we are actually doing, we have a variable, we divide it into shares and perform all the computation repeatedly
On the shares.
on the shares. So, as a analyst, I can perform the same thing on the shares also,
Yes.
and can
you
get all the ideas. So,
Yes.
do we have to change the share by time?
No. So, the shares is now depends on random, right. So, earlier it is X. If you do all this calculation, you will get X, because X is fixed, right. Your earlier it was key, right. X is basically your key. What I am doing now, random is basically a random number, right. So, if you run for 2 text, the value will be different, right. So, if you run for 1000 text plain text, if you XOR that, you basically your key is now converted into shares with random. For every text you will have a different value. So, then this correlation is not possible. So, what I was saying earlier, that your key is fixed, I run for 1000 test cases and I separate them into based on the LSB. Because the key was fixed, I get the pattern. Now, key is also changed because it depends on random. So, the correlation with the power consumption with the random is broken, right. So, you will never able to get this X0, X1, because there is no correlation of power with this X0, X1 anymore, right. So, that is the key idea, that the correlation between power versus the key is now broken, because it's become random, right? And there will be a true random number generator, it will give you random every time you encrypt. Text 1, the random will be different, text 2 value will be different. So, the key will be kind of different in every, although key is fixed, but the impact of key will be different. Got the idea, right? Okay. Any other questions? So, you have to see, I will go more detail into the technology thing, how do you optimize and all, right? But this is the baseline, you have to understand this, then only I can go next.
Sir, one doubt, sir, that since the random number is breaking the correlation, then why am I going for D plus 1? I mean, introducing 1, wouldn't that be enough?
No, it is basically the what kind of security you want to guarantee. Say for example, if you can get 2 values from internal. So, this is, you have to theoretically prove that if anybody have access to 2 locations, you won't be able to give that key, right. So, that is the deprobing sequencing concept, that if you have D location access, you create D plus 1 shares, and as I mentioned that unless you have all D plus 1 value, you won't get X. So, what is the value of D? That what kind of security you want to give, right. But in practical, usually you keep 2. I mean, people assume that you have only 1 point access, just like your S box, right. So, with that you just create x0 and x1 with 1 random, because the random number generation is also costly affair, right. So, if you use too many shares, then overhead will be too high. Okay. So, it is a design choice or the kind of security guarantee you want to give, based on that you will decide the number of shares or the value of D. So, everybody understand this? This conversion is understood, right. So, if I give you a C code, you can manually rewrite everything and can give me this version, right? Yes? Okay. So, now for my software, the high level synthesis, this is the input, right. What I am supposed to do? I want to give a circuit that is exactly doing these things, and I know exactly where I have to put the registers, that should put the register there, right. So, that should be the kind of software that should do for me, right. This is again, this register is coming because of the glitch that I have already discussed, that if this is the software version and its diagram wise this is basically, and this is this AND operation is this is your P1, right. P2 is this AND operation, P3 is this AND operation, P4 is this, then you have I1 is this XOR, this I2 is this XOR, and these 2 are this last XOR operation, right. So, effectively this code, this is the diagrammatic version, right. So, if I give you this C code, you should give me Verilog corresponding to this, right, which is very straightforward thing, right. You just write this code in terms of Verilog syntax, right. But in hardware, as I mentioned, you have to put register, you have to put 2 register here, right. So, then there will be no glitch propagation. So, in the hardware version, I have to put 2 register here to make sure that even your design is protected against glitch. Okay. Understood? And then as I mentioned, this is one of the way you implement AND gate, and these are the different possible gadgets we have, right. We can use any of them. So, you can write the C code corresponding to this, the way I write corresponding to this, right. We can have gadget, the C version of the gadget as well. So, this much everybody is able to follow, right. Now, when you have the software masking is straightforward, because you just replace things with shares, you rewrite all computation in terms of shares, that is all, right. That will give you the, and then you replace all the AND gate with the selected gadget, okay, done. But when you convert into hardware mux design, we try to use high level synthesis, because I do not want to write the code again in Verilog, right. So, I have already put my effort in making my C code mask, why I should put my extra effort to make again Verilog, right. So, this I want to develop an HLS2, as I mentioned. Just to give you an analogy, if this is the C code, this will be my Verilog code, right. So, you see that basically this will become OR. So, I will just use assign statement, and because this is becoming registered, so I just use always passage of clock, you update these values I1 and I2, right. This is the register value I1 and I2, and your output is also registered. So, I am also putting Y0 and also. So, if this is my C code, this is the corresponding Verilog code. So, if I ask you to develop a tool, you can take this and you can give me this. It is not a big deal, it is a very easy thing, right. Any of you, if you have little bit of idea of coding, you can do it in a month time, right. You can develop a software. If you give me this, I will give you this code. So, where is the challenge, right. So, it is very straightforward, looks like. Understood this one, this conversion? Yes.
Sir, we have discussed about software masking and hardware masking. Out of both of them, which is very, as compared to both of them, which is fast and efficient to use?
It depends on your application, right. So, I mean, as sir was mentioning in the previous class, that if you have a ASIC chip, right, so that has the least power, right, and it may be much efficient because it is only doing AES. When you run this code on a processor, it consumes, because it has so many other things, so it will consume lot of power and time also. So, usually if you have a design specific implementation in ASIC or FPGA, then that will be less overhead, right, and that is what the discussion we are talking about, right. So, when you try to put say encryption, suppose you have a edge device from where whatever text you give, you want to encrypt and send somewhere. So, then AES has to run there, right, you cannot run somewhere. So, you have to develop a tiny chip that will run inside that this IoT devices, right. So, that is what I am doing, basically that is why I am converting this into Verilog, right. This version will run in any processor, right, Mux version you run on any processor, it will work, right. But my objective want to create a Verilog code or the hardware that is only do AES, it will not do anything else, and it will be a very tiny chip that will be put inside in any some IoT devices or edge devices. Okay. So, everybody understand this conversion, right. So, you will basically you identify wherever there is a reg is the where you need the register, you will put those, I mean define them as reg, and then you will basically put those operations in there always, that the this Verilog convention, and other things is basically wire combinational circuit. So, this is combinational circuit, this is sequential circuit, right. But it apparently looks like that this to this is quite straightforward, right. It is, I do not see much challenge here. Okay. So, I maybe probably skip the existing work because that may not be that much important. So, as I already mentioned, so let us see if I give it to existing high level synthesis tool, say Vivado HLS or say Catapult, what will happen. So, we have identified that. So, you need exactly in this format, right. Whenever I give this code, HLS makes some modification here, which is called reassociation. It is basically if you are doing A plus B plus C, you can do A plus B followed by the result can be added with C, or you can do B plus C and the result can be added with A, same thing, right. But in hardware that is not the same. For this masking case, because you have to do this randomization with P2. What is happening here? He is doing randomization with P1 and then that is adding with P2. So, it is basically the example I give you, that A plus B plus C, you do A plus B first, then result will added with C, or you do B plus C and all. Both are same, for some reason probably to reduce the depth of the circuit and all, they did this. But because of that, the value you have to protect P2, it is not getting protected anymore. So, the security guarantee, the random number you are adding to this is gone. So, this is basically done by high level synthesis tool and we have identified that. So, this kind of modification is called code optimization. So, any HLS tool do 100 of such optimization, this is one of the example, right. You can see that code copy propagation, constant propagation, common sub expression elimination, so much of optimization that does. It is just one example and you do not know what will impact for what, right. So, this is one example, and just to highlight this high level synthesis does scheduling, allocation, binding, data path controller generation. So, the kind of hardware you are going to get, it is no more what we are supposed to get, right. I am supposed to get this, but I am going to get this. So many multiplexer will come, there will be a controller circuit and so on. So, effectively if you run with existing high level synthesis tool, what we observe that the desired hardware is not getting generated, it is giving optimized version, but this is not what I want. Okay. So, I decided to develop this masked HLS which will do this for you. Okay. So, now So, this conversion as I show you, it is quite straightforward, that you give me this code, I will give this version of the code, not this one, sorry, this version of the Verilog. But is there any challenge here, or is there any scope of optimization? Right. So, that is something we are looking for, because the transformation, as all we agreed, that it is a very straightforward one to one transformation. You take one line, either you make it combinational circuit assign, or you make it always block and put it in, say, at the rate of passage of clock, make it sequential, right. So, it is a very straightforward thing. Then is there any other optimization we can do? The answer is yes. So, that we have explored and we figured it out, and that can give you lot of benefits. Okay. So, that is something I am going to talk about now. So, suppose this is one of the circuit we identified. Okay. So, this is a one of the implementation of masked version of the circuit, okay. And it says that you add these 4 registers, that 4, 5, 12 and 9. So, this 4 register has to be put for stopping the glitch propagation. Okay. So, this is something, so this circuit is same, but for glitch propagation this 4 register has to be placed. So, now you think about 2 version of the circuit, one circuit where this 9, 4, 5, 12 is not there, these 4 registers are not there, versus this version of the circuit. Other things are same. Are these 2 circuits are same? Will their function will be same? Did you understand my question? You have one version of this circuit where these 4 registers are not placed, because this 4 register is coming because of your requirement of glitch propagation. So, you can always have a combinational circuit, there is no register, you are just doing this. So, is there any difference between these 2 versions of the circuit? Yes, no, are they same? Same, different? Why they are different? I am saying it is different. Okay. Why is the difference? Someone? Time difference obviously, but there will be time difference. So, earlier if there is no register, within 1 clock you will get the output, right. Anybody have more thought that which the functionality remains same. So, whether you are getting output in 1 clock or 2 clock is one thing, but will the functionality of this circuit will be equivalent to the circuit where there is no register? Will be same? Yes, no? It will not be same. Okay. Why? You think about the circuit where these registers are not there, if you give this input, within 1 clock output will come, right. That means the value whatever I am giving in clock 1, that value will come at output. Now, here you see that I have a register here. So, whatever value I will give in clock 1, it will store here. In only clock 2, this value will come here and will get the output, right. This will impact the output. But whereas this value A0 and B0 will get through this and go here. So, that value will come to this output in clock 1 itself, right. So, that means I am not computing the same thing, because I want to compute whatever I am giving in clock 1, they said they should be processed, right. What is going to happen here? Whatever I am giving in clock 1, that will be multiplied with the value I have given in clock 2, because clock 1 value will be stored here, this will propagate here, and then in clock 2 you will give some value that will come here, and that value will be multiplied with the value I give in the clock 1. Then the functionality gets changed, right, because the very simple design principle is that if you have a circuit, if you want to add a register somewhere, you have to add in all parallel path. That will basically increase the latency of your design by 1. Otherwise, what will happen? Some path have latency 1, some path have latency 2. Then what will happen? Some value will come earlier to the output, some value will come later to the output. The correlation between the input and output is gone, right. Understood this one? This is a very important concept.
Excuse me, sir.
Yeah, please.
Sir, so can we have a scheduler for the inputs to balance this clock delay?
I will talk about. So, this is the exact what Max HLS does. So, that in 2 minutes I will explain. Okay. So, everybody in the same page that these 2 circuits are not same, right. Then only you will be able to appreciate what I am going to do next slide. Understood? So, although the masked version say that you need 9, 4, 5 and 12 register, but if you just put only this 4 register, your circuit functionality will change. So, what I have to do? I have to add register in all parallel paths, right. So, for 4, 5 this is my parallel paths, you have to put all these registers, and for 9 and 12 this is all registers, right. So, how many registers I need now? 12, right. You count this, it is basically 12. And what is the latency? Latency is what? You know what is latency? Is when you give the input and after how many clock you will get the output. So, here what will happen in clock 1, whatever you give, it will store here, in clock 2 that will come here, right. So, that is why only after clock 2 you will get the output. So, that is why the latency is 2. So, earlier when there is no register, it will come immediately. Now, the value will get after 2 clock, but that is fine, you just get 2 after 2 clock, that do not change the functionality, only it will just you will get your output after some clock later, but you have to put this register, right, otherwise your functionality change. So, that is not allowed, right. If you are doing something now, if you change the functionality, that does not make sense, right. So, if you want to do manually, you will going to put 12 registers and the latency of the design will be 2. All agreed? That is the correct version. Only thing, the difference between this version with no other register is the latency is 2. So, only you are getting the output immediately, it will give you after 2 clock, but it will give you the same output, whatever you are going to get for earlier case, you will get the same output only after 2 clocks. Yeah, please use the mic.
Sir, like every gate will not have glitch, so this register is given only for glitch.
Yes.
So if we put register in every gate, then glitch will affect the output or it will not affect the
It's a
output?
good question. So, what your friend is asking that not all signals are glitchy, right, why you are putting all registers, right, this is your question, right. The answer is that for security aspect people are analyzed and they say ki you have to put 4, 5 and 9 and 12. So, that is necessary for security guarantee, right. For functional correctness guarantee other registers are needed. So, they are not put to stop glitch, but to make your circuit functionally equivalent, and that I have already able to explain, right, why these two will be the functional equivalent, right. So, the first these 4 is the necessity, the other one is have to add to make the functionality same. Okay. But so if somebody do manually, he will put register everywhere. So, 12 register, latency 2. So, the question that we asked, do you need all of them? What I effectively need? I want to make sure that all path should have same number of register. The latency is that. So, if you take any path, so this is one path, right. So, if you take this, so now this path has 2 registers 1 and 9, this path has 2 register 2 and 9. If you take this path, then also it has 4 and 10. So, you take any path in the design from input to output, there are 2 registers. So, then it is correct design, right. So, my objective is to make sure that all path in my design should have same number of register, right, but nobody told me that you need to add all 12. Can I do the same guarantee with less number of register? So, that is the question, right. And if you look carefully, you need to just 2 additional register 3 and 6, that would suffice. If you come back here, you see the problem was happening to this path, right. So, if you put some register here, then this path will also have 1 register, right. So, if you take this path, it has 1 register, but if you take this path, has 0 register. So, if you just put 1, that is done, and if you take this path, this is also have 0 register, you put it 1 here, that is done, but rest of the path has already 1 register. So, ideally I do not need to put all 12 registers or 8 extra register, 4 is necessity, 4 other 8 is basically I am bound to add to make the functionality same. But what we have shown that you do not need to add all 12, rather you just add 3 and 6, that is sufficient. Sorry. Where is the full screen? Huh? Yeah, sorry, it's too smart, right? And it's not allowing me to write also. That's why I'm explaining everything without things. It is a PDF, and it's not allowing me to write there. Okay, so I'll quickly scroll down this. So everybody understand this, that earlier all path does not have all registers. If you do this, that will make all path has 2 registers, which is good, but this make all path has 1 register. So that is what I need, right? I have to make sure that all path has same number of register. Nobody told that all path have 2 register. So this is the optimization of opportunity, that when you try to balance the parallel path, this is called register balancing. Whenever you add a register somewhere, you have to make sure that your other path are also balanced, right? So if you do this, I am saving 1 latency, I can get my output in 1 clock, and I am saving 6 registers, right? So that is the core idea of what we are doing, right? So we are trying making sure that given this location of the register, we develop an algorithm that will automatically insert the register only the minimum number of register in parallel paths and make sure that design functionality remains same, right? This is what we have done. And I am not, so basically these registers are not needed effectively, right? Those dotted one are not needed, that is the saving we have. Okay. So this is what we did. I do not want to go into the algorithm. So we basically use retiming to do that, solve that problem, but that is I think not needed in this, So we basically develop an automatic algorithm that will identify what is the minimum number of registers you need or minimum latency you need, and based on that it propagate the register to these paths and make the all path balance, right. So that is the model of the story. So we just keep all those slides, is basically the algorithm, right. So we are how we have done that. So but I think that detail is not needed in this forum. So we basically make sure that when you give me this circuit, I will add register in parallel path as well. Okay. So this is the overall flow then, right. So you have the masked gadget version of the code. I will identify what is the minimum latency, then I will automatically balance all parallel path and add registers. Then I convert them into Verilog code, because you all agreed with me that converting C code into Verilog is straightforward. Only thing is that this is the interesting problem. How do you identify what is the minimum latency, whether 1 or 2, whether you need 12 register or 6 register. So that is the interesting point, and that is the optimization opportunity in this tool, and that is where our contribution, right. Yeah.
Sir, we have talked about number of registers that we are going to put, but what is about the value? The value of all registers are to be same, or they can be different according to the glitches?
No. So yeah, I understand the question. So registers is basically a memory in your design, right. So you have to initialize everybody to 0. So there is a basically when you write a Verilog code, you just have a reset. You just at the start of your implementation, you reset value will be stored. Okay. Any other question? Understanding of the work. Okay. So this is the idea that you give this marks code, I will give you the marks Verilog code based on this flow. But I have to prove that the first thing I will show you that this actually gives lot of improvement. So we have shown that the manual where you add this all 12 registers and 2 latency versus the version we generate can save up to 73 or 74% of registers in your design and almost 45% of latency, right. So that we have shown for 2 S box, one is present and one is that AES S box that I talked about. Okay. So here is the kind of result. So when you have this and we can use many other gadgets, right, DOM and HPC1 and COMOD. With that, this is the kind of, but the runtime of the tool is small and the code number of lines code of generated is okay. So we are able to generate a automatic version with our tool, right, and it is open source. So this is important. So this is where the overhead that we are talking about, right. So what is the overhead? So if you see here that this is present unmasked, this is the total area, and this is with different domain, different gadget, and you see that HPC1, HPC2 they have more area, right, the circuit size was bigger, right. So we have shown that almost overhead is basically 3x, right, and for AES it is kind of 7x. So this is the kind of overhead, and timing actually improved because you are adding a register in between. So, your delay of the path will reduce and you can run it much faster clock now. So, the timing has improved, right, by. So, earlier delay was say 19 nanosecond, sorry 28 nanosecond, that become 5.7 because you are adding registers, right. So, that is the kind of benefits in terms of this timing, and this is important. So, if you do manually adding all register in all path, this is the number of register you are going to add, and you can see for AES with Comar gadget manually you would have added 15,000 register, right, where we are doing only kind of 3,000, right. This is the kind of benefit you are getting, although it looks very simple, but this can give you this much of saving in terms of registers as well as the latency. Most of the cases latency is half, right, 13 to 7, 25 to 13, 9 to 5 and so on, right. So, this is the kind of benefit that Mux HLS gives over conventional HLS tool. Understood? But yes, please. Yeah, sure. So, so this is done, and this is the again overhead data. So, in general 74% register reduction and latency is 45%, but I have to prove that the generated design is secure, right. That is very important task, and that is done by TVLA, and Professor Mishra will talk about the TVLA process in more detail. It is basically test vector leakage assessment. We have 1 hour classes by Professor Mishra on that. So, it is basically and this is the tool flow which can be used to identify the traces. I can explain you. So, basically you have this implementation, you run on you basically synthesis with synopsis, then you get simulate with test bench with VCS, then you will get the simulation file VCD file, you do this prime time analysis, then with custom view you get the power number, right, and then you do the TVLS testing to see whether you have a leakage or not, and it basically says that if your the value you are going to get within plus minus 4.5, it is safe, there is no leakage, right. This is it has been shown empirically, right. So, now let us see for present what is happening. So, the and this y axis is the number of traces. So, the number of traces is less, that means you can easily break that, right. So, original AES without any masking we are able to break in kind of 3000 traces. Okay. When we put it this present domain and we generate the Verilog, and we are able to break, I mean store it up to 220k. So, from 3000 to 220k, right, to 220,000 you can understand, right. This is protection, and if you go further and if you use say Comar, you are able to protect up to 1.6 million, which is quite safe implementation, right. So, this shows that. So, basically for other also we have shown, and similarly for AES also the initial one was broken is around 3000 or 4000 traces, but when you use say DOM, we are able to protect up to 1 million, for HPC 1 up to 30 million, for HPC 2 it is up to 40 million, and for Comar is basically up to 100 million, right. So, basically it is safe, nobody can break it, right. So, Comar is the most powerful one, right. But this shows that this tool is able to optimize the resource and give the protection, right, and it is automated process. You just give me the C code, I will give you the Verilog, right, and it is guaranteed to be correct. Okay. So, that was all from this work, and you can actually search, and you this the source code and everything is online. So, you can just use the tool for your research. Okay. So, this is one part. Now, I will move to the next part of this talk where I talked about give me 2 minutes. So, as we have discussed that your friend talked about that this masking has lot of overhead. Okay. So, can other technique be used? Okay. So, that is the another research we have done, which is basically can I modify my circuits such a way that the modified version is more secure as compared to the original version. Obviously, it is not give you as good as protection as masking will give, but we have shown that it gives good enough protection, right. So, if it is sending 500k, 600k traces, it is safe, people will not able to break those kind of implementation. Okay. So, it is basically we try to use various circuit transformation to protect our design without masking. So, no masking is used here. Okay. So, the masking part I skip. So, masking give good protection, but same slides, but it has lot of overhead, right. So, we basically we have shown that this is what I was talking about. If you make a Komar version of AES, it will have 40x overhead, right. So, it is basically if your original AES versus a masked version, it has 40 times more area, right, 5 times more latency and 18 random numbers. This is the kind of overhead of masking. Some cases specifically for edge device and IoT devices, that is not acceptable, right. So, let us see what we have done. So, what we have done is basically interesting. So, we in the Verilog code we identify what are the sensitive registers, just like the that attack perspective where people try to make the attack, right. Those are the sensitive locations. We identify that, then we have applied 3 kind of optimization. One is called sub circuit duplication. You take some part of the circuit, duplicate it, then there is a bubble pushing, I will talk about that. Its bubble is nothing but NOT gate. You put 2 NOT gate in any position, the circuit will remain same, right, and then you move that NOT gate here in the circuit structure will change. And then we have used register, you have to register in some places, and then you have to balance register, right. Anywhere you add register, balancing everybody now understood, and then you have done clock gating, right. So, this is kind of controllable, you can control these things, and we have shown that the tool that you have developed can give you a good protected version and has less overhead as compared to masking. Okay. So, I will talk about it with example probably and quickly show through what is all these steps all about. Okay. And you can actually take plug and play kind of thing, you can use some of them or may not use, right, you do not need to use all of them, right. So, that is what this diagram talks about. So, let us say I have this design with me and somehow we identified this is the register which is sensitive. So, I should add more protection in register R3. So, this is the first step, the identifying the sensitive registers. Okay. And this is the kind of sub circuit, right. So, you have this sub circuit. So, this is the kind of cone of influence for this register, right. So, this is the sub circuit identification, right. Then what is the duplication? You just create 2 copies of the circuit. Okay. So, it is basically you have this is the sub circuit, you basically create 2 copies, right. So, this is the copy 1, this is copy 2. Okay. And you connect with the multiplexers, right, there is a mux here, and this multiplexer will be controlled by some random input. Okay. So, either this I will talk about more. So, either this circuit will work or this circuit will work, the core idea is that, and this is duplication, you can create multiple copy also 4 copy, 6 copy, whatever it is. Understood what I am doing? You take sub circuit, you create 2 copies and you multiplex them. So, in randomly, because you are randomly selecting between them, if you run once it may be selected this, next time it might select this, right. So, that is the kind of idea. Okay. And if you create 4 copy, then multiplex will be 4:1, then there will be 2 bit of random, right. So, based on then there will be, it can select one of the 4, right. Everybody understand this? Okay. So, this is what we do, but you should ask me this question that these 2 circuits are same, how does it matter you create the copy, right. So, purpose of creating the copy is not that you will keep the same circuit, I will try to make modification in these 2 copies. 2 copies should behave differently in context of power, because I want to give protection against power, right. So, I want to make modification in these 2 copies, so that their behavior, power behavior will be different. So, that is the objective, that is why I am creating the copy, right. So, so basically now what I am going to do, and how do I do that? Using bubble pushing. So, I can randomly pick some location, say I pick these 2 location in this design, and in this design I pick this location, right. Randomly I will pick the locations, I will put 2 NOT gates, Okay. So, I put 2 NOT gates here. So, there is no change in the circuit. So, I want to make sure the circuit functionality remains same whatever modification I do, right. So, here I just put 2 NOT gate here. So, then circuit will remain same. Then we will move this bubble or the NOT gate across this. So, if you have an AND gate and there is an output at not output, and if you put it here, this AND gate will become OR gate, right. So, the circuit will change. Okay. So, I will basically do that, right. So, if you do this, if you put 2 NOT gates here, if you convert, one NOT gate will move this direction and this become OR gate and 2 NOT will come here. So, then the circuit is now different, right. This is AND gate and this become OR gate, right. And this is, I am just giving a small example of 3 gates. You think about a subcircuit of 20 such gates and you put 10 bubbles and move them around, there will be a lot of difference in the circuit, right. Many changes will happen. And here I am showing in terms of gates, but if you have say the same example here. So, if you have a say OR gate, if you put 2 NOT gates and you convert, this will become AND gate, right. If this was AND gate, 2 NOT gates you can move, this will become AND gate, right. So, this way you make lot of changes in these 2 copy. That is the bottom line idea, that you make sure that these 2 circuit is sufficiently different, right. Why I am doing this? Because in general, in high level, in power consumption depends on how many times your value move from 0 to 1 and 1 to 0, right. That basically the transition from 0 to 1 and 1 to 0. If the gates are different, the transition will be different, right. So, then the dynamic power consumption will be different, that is the core intuition. Then what I will do? I will do now this bubble pushing is done, right. So, this we understood. Then now what I will do? The register insertion. So, next is register insertion, and why I should add register? To stop the glitch propagation, that I have already discussed, right. So, what I can do again? I can randomly place registers. So, here I decided to place register here and here and here. Here I just put 2 registers, something like this. So, you randomly place registers, but whenever you place register, you have to do the balancing, that I have already discussed, and that I have already told, right. I have already told that if you tell me that you add a register, it will automatically identify where else you have to add registers. So, I have already software that will do that parameter automatically, right. So, we insert register random location, so that glitch propagation also different, and glitch also consume power. So, the glitch of 2 circuit will be also different now. So, we have 2 circuit have different power consumption and glitch propagation. So, I want to make sufficiently different circuit, that is my whole objective, right. So, this is what I have done. Then what I will do? When I am trying to run this part, I want to make sure that this part should not have any transition, then the power consumption will be same, right. It does not matter which one is running. If you run both of them, then what will happen? There will be toggle here, there will be toggle here, right. So, what I want to do? I want to add a clock gating, this is my clock, right. So, this clock is coming here and I connect this clock with this random number, right. So, I am connecting this and I AND this, and that will become my clock. And what will happen to this? You understand what is clock gating? Now, whenever this RAND is 1, then this will be 1, right, and this will be 0. Right, because I am putting a NOT of this. So, if the RAND is 1, then this part of the circuit will work, because this will become 0, right. There will be no clock here. If there is no clock, then no value will stored here, right. And if I put this random value 0, then this will become 1, this will become 0. So, then this circuit will work and this circuit there will be no transition. That is the core idea effectively, right. So, this way you can actually control the power consumption of these 2 copies. That is all, right. So, from this version I will create this version, right. So, this is the original circuit, this is my modified circuit where all the gates has been changed. I have 2 copies, it can have multiple copies, copy has a different functionality, different number of registers in different places, and they are also gated. So, this version I will give you, okay, from this version. Understood? Any question? Everybody understand the core concept? So, if as long as you understand the overall idea, that's good enough, right. Understood? Okay. And in general, why this is secure? Basically, it is saying that if you if you have create k copies. So, it is basically saying that if you have a circuit C, I have a path P, k sensitive register, it is not only one register, you can have multiple such registers, right. And if there are, you are creating duplication is n, so you have n to the power k possible path now, right. So, as a result one of them will be executed. So, there are, you have to basically try for n to the power k possible cases, then only you will able to make some assumption, right. So, that is the kind of idea. And this, as I mentioned, this you have control level, you can actually decide how much depth you want to duplicate, whether you want to take the entire circuit or part of the circuit. So, that is the degree of duplication, how many copy you want to create, how much, what is the depth of your bubble pushing, and then you can select a subset of this optimization, right. So, you can say ki I want to create 2 copies, I want to create 4 copies, and then that will do this, right. So, this is the overall thing. Then bubble pushing depth also is another thing, that whether you want to push the bubble only one level or you want to go 10 levels, right. So, that also you can control. And just to give you the idea that bubble pushing when you do say in a adder, right. So, if you have a adder here, so gates understood. If you have a bubble at the output of a adder, the modified circuit will be this, right. If you have a multiplier, this we have shown here mathematically why this will be this, right. If you have a subtractor, it will look like this. Okay. If you have a multiplier, the modified circuit will be this, right. If there is a multiplier, the modified circuit will have one multiplier, but there will be a shifter, there will be adder and all, right. So, there will be a lot of changes, right. If you want to do this modification in the register transfer level where you have multiplier adder, the changes will be significant. It is just not AND gate become OR gate, right. So, that is the kind of idea. So, this is the algorithm. So, I will just keep. So, here is again a complete example that if you have this circuit and if you take this multiplier, this will become this. If you take this adder and you push here, so this will become this, and if you push both of them here, there will be two round of things, and this one adder will become this, right. So, this is the kind of modification is going to happen because of bubble pushing in your circuit. Okay. And also you can actually do a sub circuit modification in the sense that if you try to take, this is your sensitive register, you can take the entire thing, or I will say I will only take up to this C2, right. So, I can only copy this much. So, that will give you less overhead, because if you take the entire circuit and you create a copy, this will be the circuit, right. Whereas, if I only copy this much, I will only have 2 copies, right. So, this kind of overhead you can control. And those, and then again the same TVLA flow I have used to show that whether it is protected or not, and the results will be interesting, right. So, here this is the power traces obtained when you are running the design. The unprotected one, there is a lot of difference, right. This is the, so when you are this is the power traces, and when you basically run with register pushing, so you basically the difference is less, right. So, it basically goes off here, right. And when you do this bubble pushing and duplication, so you basically make it random, right. You cannot differentiate between these two, right. So, this is basically the power profile of the protected design, and you will not able to see here, you can easily make the difference between this and this, right. What is happening here and what is happening, you can make a difference, but here it will be difficult to differentiate between these two, right. That is the kind of randomization is happening in your design. Okay. So, same designs you have taken, transpose and all, and this I have already talked about that. It is basically when we are doing this S box TVLA for present with different kind of so this is basically for only for duplication and bubble pushing, right. So, this is giving protection up to 822K, this is giving protection up to 700K, where you are doing the full circuit duplication plus bubble pushing and register pushing, right. So, all this controllable, and this is giving 200K when you are doing only register pushing, right. And the unprotected one is, as you mentioned, that is kind of 2K. So, we can see that we have protection, right. So, we have up to 700K protections as compared to 2K 2000, right. Same thing for AES you have done, you are basically shown that you are able to give up to 600K or 1 million also in this case, right, when you use all of the techniques, and the original one is again breakable in 2K. So, it shows that this kind of circuit modification without any masking give you protection, right. So, that is the kind of takeaway from this discussion. And overhead is important. So, you have this unprotected is kind of 3K. So, when you do this complete masked version using DOM, so you get area overhead is 5.8 that I have shown you earlier, and protection is up to 200K, right. So, with our technique, so with only register pushing and balancing, we are almost get the similar protection, right, 200K, and area overhead is half, right. So, we are able to show that with our technique compared to masking can give comparable protection, not exactly same, but area overhead is less, right, and same story goes for AES also. So, this is basically AES mask implementation, which gives you up to 1 million traces protection, and area overhead is 27x, right. Comar is 40x, but this is 27x, and with our this 3 technique we are giving 830K, which is kind of comparable, right, but area overhead is half, right, compared to this. So, that shows that our this circuit modification technique can be good way to protect your design with less overhead, specifically for this edge and IoT devices. Okay. Any questions? So, I am done with the overall idea. So, you can take couple of questions if you want. Any questions on the technique, on the results?
Sir, one question was there, sir.
Please.
Sir, this like the traces which we understood, for a simple one it is about 2K traces and we can increase it to 1 million. Just to get a perspective, how much time does a trace take so that you can
So,
get
that is
an
what I am saying.
idea?
So, 1 million is kind of, I have asked with very serious security experts, 1 million is a very safe thing. So, in feasible time you will not able to break it. So, up to 500, 600K if you do, so some logical way it will be difficult, hard to break, right. So, that way 500, 600K is also good protection. See, you cannot make your edge device fully protected up to 30 million, right, you do not need that, and if you do that, then you have to use COMAD with masking that have 40x overhead, right. So, this trade off is there, but I have asked security expert, they say ki 1 million is a very, very safe design. So, 700, 800 is also a good number. Okay. So, I conclude here, I think I am on time. Thank you. So, we will have break now, we will again assemble after 2 hours, right, 2:30. Okay. Thank you. Okay, so welcome back. So in this particular session, I will talk about the developing efficient ML accelerators and then how LLM can help there. Okay. So in the context of the course, this ML is something is being used, right. So you kind of create some machine learning model for say some cyber security attack detections and all, and then you want to put it into that edge devices and all, right, and that is what is called accelerator, right. So it basically try to execute it on some hardware, and you want to create a application specific hardware in the sense that it only execute that particular trained model, right. So here as I mentioned, it is not on the training part, it is basically once you have trained model on some data sets and all, that model I want to run there to infer something, right, for classification or all the other machine learning tasks. So basically it is on for inference. Okay. So that is something we will talk about, and so in now I will basically to talk more detail on high level synthesis, right. So in the first half I talked about that once I use high level synthesis, the conventional high level synthesis for developing secure cryptographic implementations, we found that they are not good enough, right. They do too much of modifications and that is counterproductive, right. But in the context of this ML accelerator design, that high level synthesis has huge role, I would say, because you think about that a trained model, what is that? It is basically a Python code, right. It has certain, as Professor Mishra was mentioning, it is basically it is kind of a deep learning model. You have lot of neurons, there are multiple layers, and each layer there are lot of neurons and they are connected to each other, right. And it was something Wi into Xi, some that multiplication is happening there, the weights and biases. So that is a Python code, right. And hardware implementation means you need a hardware this Verilog implementation or VHDL implementation in register transfer level design. So what is the choice you have? One is the same way that you see that code and you write your design, that too time consuming, right. In this fast world, everybody want to press for time, they want to develop this design as soon as possible, right. So developing those Verilog or the RTL design directly for this your architecture is time consuming and it is not something a viable approach. On the other hand, this high level synthesis is exactly for designed for this purpose, right here. So for developing this ML accelerator, high level synthesis is a good fit. Okay. So we should utilize this high level synthesis in this process. Understood? So then we should know what is high level synthesis in a nutshell, right. So I think the term high level synthesis is not maybe familiar with you if you are not working in this domain. So what I will do at the start, I will just give a brief maybe 5 minutes, 7 minutes overview of high level synthesis, what it happened internally, right, what this tool does essentially to convert a C code into RTL code, right, register transfer level design. And then we will identify where actually what is the kind of difficulty in using this high level synthesis in developing machine learning accelerator, and we will identify those limitations or the difficulties or manual involvement. And nowadays LLM is being used to make many mechanical job automate, right. It basically can be used to automate many mechanical tasks, right. So we will basically see how LLM can help in this high level synthesis process, whatever the manual involvement there, how can LLM help in this process and make that process faster, right. So that your overall time to design a ML accelerator is reduced. Okay. And then we will talk about this how do you actually do this process with LLM plus HLS, and then some results and future direction. Okay. Any questions so far? Okay. So this I think I do not need to give more emphasis that nowadays deep learning algorithms inference is happening on edge or IoT devices, it is something well known, right. So we I think we are all convinced at this point, and I do not want to give more focus on that, why we should do that. And there are some recent work which I just connected here, which basically targeting either for ASIC or FPGA targets, right. So, this there are a lot of already effort, it is not that I am the first person talking about this, right. If you open this domain, there are a lot of research, people try to do many ways. Okay. So, what do you mean by this hardware acceleration? So, when you try to put this, so this figure is actually important for you. Once you try to have a this model which is trained, if you try to put it into hardware, and if your what you try to do there, you try to make it lightweight, right. So, you all talk about that, I do not want to make a very high overhead or high latency design, right. So, there are many ways I try to minimize the size, and sir was saying that the one option is that you identify some of the nodes which is not so important and remove them. So, size of the model will reduce, right. That is one way of approach. The other very important approach is basically this quantization, right. So, this quantization is basically it talks about that your actual weights, right, may be 32 bits. What about using 8 bit version of that, right. So, that means straightway your size will be 4x less, right. So, that is the one idea that you try to quantize to 8 bit or 16 bit or 4 bit, whatever is needed, without much compromising the accuracy. So, actual accuracy may be 99%, it become 98%, 97%, which is okay type, right, but area overhead become 1/4, right. So, that is one approach, and the model pruning is the other thing what Professor Mishra was talking about, that you try to discard the nodes or the weights, that is not so important. Okay. So, this is being done, and say somebody has already done that, and you have given that version of the code, right, before high level synthesis. So, so what I will do, as I mentioned, that I will talk about high level synthesis with more detail. I mean, what is, it is not a magic, right, it is basically a algorithmic steps through which you can convert a C++ behavior into register transfer level behavior. Okay. And the advantage I have already talked about, the certain design cycles, that it will reduce the time, because if you write your Verilog code, it will take lot of time, and it is just a minute, right, within minutes you can get this in. This is another very important advantage of this high level synthesis, which is called design space exploration, is from the same specification I can develop a design which has less power, I can develop another design which has less latency, I can develop another design which has area latency trade off and have a balanced version of that. All those is possible, and that is called design space exploration, right. With high level synthesis, just changing few parameters you can do that. So, from the same C++ model, I can create a RTL which is very low power, I can create another design within few minutes which has very less area, and so on, which is almost double effort when you try to do directly in RTL, because I develop something low power, that version I cannot tweak and make latency intensive, right. So, you have to start from fresh, which is not needed in high level synthesis. Okay. And it has lot of such optimization, you have to just use them to do this, right. So, this is the advantage. The steps there in high level synthesis is, first is compilation. I will not give in much detail, but I think it is a good idea to see what happening inside in this box of high level synthesis. It has allocation, binding, scheduling, and then data path and controller generation, and it will give you the RTL. Okay. So, I will just walk through an example with some diagrams to show you that what happened internally. So, C version, so the Python and C, I can convert a Python code into C code, right. So, there are converters. So, you can think about that, I have a C version of the model with you. Okay. So, so how a C program runs? If I give a 10 line of codes, how it happens? The first line execute, then the second line, then third line, and so on, right. It is kind of a top down, right, sequential execution. But in the hardware, if you have two, say, adder in your design, what will happen? So, suppose you have two adder, some data is coming here and it is going somewhere. So, if there are two adders, in every clock you can do two operations, right. Basically, hardware is inherently parallel, right, whereas your C++ code is inherently sequential. So, the model of execution of hardware versus software is different, right. So, the way your C code execute in your processor also, that sequential nature. So, that is a fundamental difference. And the second thing is, a timed behavior, that as I discussed in the first half also, that whenever you have given in something, you have to tell what exactly happening in clock 1, then in what exactly happening in clock 2 and so on, right. This is basically time. I can tell that in time clock this will only happen in this design, nothing else will happen and so on. Whereas in C there is no concept of time, it is an untimed behavior, it is just top down execution, right. So, it is not very trivial to convert a C code into RTL. It is basically functionally equivalent, but their model of execution is different, their timing behavior is different, but still they both perform the same thing. If you give the input to this C code, whatever output you will get, you give the same input to this RTL design, that will give you the same output, right. That is the kind of objective, but this transformation, unlike whatever you discussed in the first half, it is not trivial, right. Lot of decision making is happening inside, and I will just walk through you through this process. Okay. Just to give you some feeling that how it looks like. So, you basically have a C code like this, where you have a while loop, set of statements, and then it is happening in the loop and all. Whereas, if you see a Verilog code, just I took it because if you take this code and if you convert it into Verilog, there may be 100 line of code. So, I just took some of them. We are saying that if this passage of clock, if this you are in this state, then you update only this register, right. If you are in this state, then you do this, you just reset this register and so on, right. This is the wire transfer, this is the conventional operations. Here you are saying that if this is the state 2 and if your this condition is hold, then you go to state 1, otherwise you go to state 3. So, this is how your Verilog will look like, right. This is does not have any correlation with this apparently, but these are they are the same thing, right. So, how can I convert this into that? That is the question, and that high level synthesis does very efficiently. Okay. So, what I will do is, so basically your RTL will look like this. You have a data path where you have set of function units, set of registers, they are connected, the output is going back to registers. And why, by the way, this called register transfer level, and can anybody tell me why this name of this design is register transfer level design? Can anybody explain me? Any idea? Because what is happening here, in every clock, value of registers coming to this function unit, operation is done, go back to register, right. So, the transfer of value from register to register, right. That is why this is register transfer level behavior. So, I am explaining everything in terms of how your registers getting updated in every clock in terms of input and the register values. Understood? So, effectively if you have this code, this will convert into this, and structurally you will have a data path that will execute these operations, and there will be a controller that will effectively control these operations. And the first important thing is that you cannot do everything in one clock, right. You have to do in multiple clocks. So, that is the first decision. You have decided, say that I need 4 clocks, say, to execute this. So, based on that, it will say that clock 1 it sets some signals to this, so that a specific set of operation will execute here. Clock 2, suppose you decided that I will do this part in clock 1, this part in clock 2, this part in clock 3, this part in clock 4, and this is in clock 5. Accordingly, it will send the signal, so that same data path can execute this in clock 1, this in clock 2, and so on, right. So, this is how the overall structure of your design. Okay. So, I will just quickly go through what are the steps, how do you basically do that. So, as I mentioned that you have this behavior, you cannot execute, the first decision is that you cannot execute everything in one clock, then your circuit will be not feasible. So, the first decision is that you figure it out the basic structure of your design. So, it is basically say that CDFG, control and data flow graph, what is how the control flows among this behavior. So, this is basically your V1, right, and then once it is done, then you probably do the output Y, that is your B2, and this reading part is basically B1, right. So, this is the control flow, right. So, this is the while loop, when it is done, then it will go to B2, right. And then within this among this operation, what you do, you identify what is the data dependency among them, right. So, you break this bigger expression into smaller expression. So, this bigger expression you do not know how to execute. So, what I do, I break this into smaller expression. What I did, I just say that this value I will store in T1, I will take this value I will store in T2, I will take 3 this 3 into y I will store in T3, and then u into dx into T4 and so on, right. This is how I break the entire behavior into smaller code. So, that I can tell that you do this part of the code in clock 1, this part in clock 2, this part in clock 3 and so on, right. So, that is actually help you to, if you break the bigger expression into smaller 3 address code, then you can tell which operation is going to happen in which clock, right. So, this is what happened inside the tool. So, tool actually does that, right, and then it identify the dependency. This is the dependency. What is the dependency? Why the dependency is coming? So, you see this is you are doing this T1 equal to this, and here you are using T1, right. So, until, so this value is coming here, right. So, you are doing this this is T1 and that value is coming here to calculate T5. So, that means until this operation is being done, you cannot execute this operation, right, because there is a dependency from this one, and similarly from this operation also there is a dependency to this, and this is exactly showing that, right. For this operation, this is your T1, this is your T2, and they are coming here, right. So, this dependency, why it is important? It says that in which order you should does this operation, right. I cannot execute this operation until these two are done, right. I cannot do this operation until this is done. I cannot do this operation until this is done. So, this basically tell you the order in which you execute the operations, right. So, you can tell now, once you have this dependency, you can tell that I will do this operation in clock 1, this operation in clock 2, this operation in clock 3, and this operation in clock 4, right. So, this is what is called scheduling. Get my point? Any question? So, the tool actually does that, it identify the smaller operation, identify the dependency, based on the dependency it decide how many clock cycle I need to execute this behavior, right. This is what is called scheduling. So, this is done. So, once the scheduling is done, what I have to do? I have to decide how many multiplier I need, how many adder I need, how many register I need, right. So, basic intuition is what? The trivial way that how many multiplication operation is there, you use this many multiplier, but is it a good design? No, right. So, you have 1, 2, 3, 4, 5, 6 multipliers. Should I use 5 multipliers or can I use less? Can I use less multiplier for this? How? Any idea? When I can use the same multiplier to do more than one operation, right? Any idea from anybody that this is how I can use a multiplier to do 2 multiplication operation? Anyone? Some intuition should come, you should tell me. If this is my schedule, I am saying that this 4 operation is going to happen in clock 1, this 3 operation is going to happen in clock 2. So, can I do operation of clock 1 and clock 2 with the same multiplier? Right, right. So, that is the idea, sharing. Whenever whatever the multiplication happening here, they are working in parallel, right. So, you need basically 3 multiplier 1, 2 and 3, but once that clock is done, that multiplier is free. So, what I can do, I can take this multiplier and use, I can do this multiplication with the same multiplier, right. Similarly, this I can do with the same multiplier, right. So, this is how I can do the sharing. So, in this case I need how many multipliers? 3, because this is the maximum number of multiplier needed in one clock is 3. So, the tool exactly does that. So, it identify the parallel operations, and those are called non-compatible, right. So, they are basically working in parallel. So, they are conflicting operation, and 2 operations they are happening in 2 different clock, they are compatible. So, they can be done with this. So, you can actually map this problem in a graph coloring problem, and you can solve this problem and identify how many multipliers is needed, right. So, what about register? How many variables we have here? T1, T2, if you go back here. So, T1, T2, you have basically T1, T2, this variable plus u, dx and all, right. So, one trivial solution is that you use one register to store one value, right. That is the obvious solution. But again I will ask the same question, can I reduce the number of register? Similar concept. How? Yeah, so exactly. So basically for a variable, I have to see what is the lifetime of the variable, when it is defined, when it is last used, right. So for example, T1 it is defined here, right, and it is used here. So the lifetime of T1 is basically this. So it's you need to store this value of T1 in only for S2 clock cycle. I don't need to store it anywhere else, right. So now if two variables, say for example now T5, it is lifetime is this. So I now you can use the same register to store both T1 and T5, because in clock 1 I will store T1 valued into this register, and in this S3 I will use the same register to store T5. Understood? So this is the decision, that what is the minimum number of multiplier I need, what is the minimum number of register I need, what is the minimum number of adder I need. These are the decision, but this is a systematic algorithmic process, right. The tool can do these things automatically, and it is basically algorithm, right. You can identify the lifetime of the variable and you can do that, right. So if you saw here, I actually did that actually. This is the lifetime of T1, this is lifetime of T3, and this is lifetime of T3, T5, sorry T6. So I can store this T1, T3 and T6 into the same register, right, because they have a non overlapping. So this is how we can actually identify. Understood? So this is the decision is happening there. So you first the tool identify what is the number of clock needed, then the schedule, based on the schedule they identify what is the number of multiplier needed, how many adder needed, how many register needed. Understood? So this happens for all operations, and then what you basically got here, that you basically identify that you need basically 3 multiplier, 1 adder, 1 comparator and few registers, right. So that is the optimization. Okay. And then what happened, you have to these are the multiplier, these are the register, you have to make the connections, right. So what you will do effectively, you know that in this clock 1, now this is the operation is happening. Okay. So you have this multiplied 1, so this is your multiplied 1, this is your R5, yeah. So this is your R5 and this is your R7. So you have to make a connection from R5 to this and R7 to this, right. This is the connection you have to do, and the output is going to R1, right. This is go back to R1, right. So this way you read this operation and make the connections, right. Is it possible? This is in clock 1. Now when you move to the clock 2, what will happen? Now the same multiplier being used to compute this operation, right. Earlier R5 was coming, now R1 is coming, right. So what you have to do? You have to multiplex the input, right. So this is now earlier R5 was coming, now R1 is coming. So I add this multiplier, right, and there is a control signal here, which will be in first clock it will be 0, second clock it will be 1. So that in the first clock R5 goes here, second clock R1 goes there, and so that in the first clock R5 into R7 happens, and similarly in the next clock R1 into R2 happens. Got the idea? So this is how you can make the connections and you get your data path, right. So this is the final data path for the design I have taken. Okay. And then these are the control signals, right. These are the control signals. So this value will come from the controller. These are the control signals. So you will tell that in the first clock you send here 0, so that R5 come here and R7 comes here and so on, right. So the controller value will be determined by that way. So these are the, so in controls S1, this will be your control signal, so that these 4 operation can execute in the data path, right. In S2 this will be your control signal, so that these 3 operation can execute in the data path, right. So this is how your final structure will happen. This is your data path and this is your controller. The controller has this 4 state, and this is the loop, and this is your first block B1 and this is your B2, right. So, if you club these two, this and this, they will together will execute what? That for while loop that I have taken. You got the idea? So, this is what exactly happened in high level synthesis. This is not a magic, it does everything step by step. Any questions so far? Clear? Any question? I am going little bit faster because there are a lot of algorithms involved, but I just want to walk through with the process. So, this is the flow, and as I mentioned, within high level synthesis you have many optimization also. You can actually pipeline a loop, you can unroll a loop, you can partition an array, there are data flow, there are function pipeline, there are many optimizations that also you can apply, right. So, I am not showing what will be the impact, but you can do that, and that will give you different combinations. So, for example, pipeline give you latency optimized design with little bit more hardware, right. If you unroll, it will basically area will explore, but your latency will be minimum, right. So, these are all very well known studied thing. Okay. So, this you can also apply high level synthesis with, you just instruct the tool that you unroll this loop, pipeline this loop, it will do that for you. Okay. So far everything understood, right. So, now, but we are discussing ML accelerator. So, now what we want to do? I want to use this high level synthesis which will internally do all those things to give me a hardware, okay. And my objective is to use it efficiently. Okay. So, if you have a C++, so suppose you have a Python code, this is your ML model, right. Then you have a Python to C converter. So, that will give you C, because this HLS tool will, it basically does the from C. Okay. So, this is how you can, starting from any machine learning model, you can generate the Verilog code, okay. And this is the HLS tool, and that will give you the RTL. Okay. So, that is the flow. So, you can actually use the tool, and if you download this Viva HLS, which is basically free, you take any model, you can do this, you will get a Verilog code, then you have basically hardware corresponding to the ML model. Now, the question is that we talked about that how LLM helps here, right. So, everybody know what is LLM, large language model, you are using, right, ChatGPT and DeepSeek, everything, right. So, the question that we are asking, in this flow, can LLM help you in developing the efficient hardware for the ML model quickly? Okay. So, let us see why we want to do it. So, now let us identify what is the manual effort in this process. So, this tool is automated, right, this HLS tool is automated, right, you do not need to do anything, you have to just give the input, it will automatically compile, although I have shown all the steps, but you do not need to do anything, you have to give a C code, it will give a Verilog code in a minute. So, then where is the manual efforts? I will talk about them now. Okay. So, whenever you convert this Python code into C++ code, that code may not be synthesizable, right. HLS tool may not be able to synthesize it properly, because there are certain things which you cannot generate hardware for that. For example, recursive function, right, you do not know how many times the loop that function will execute. In hardware you cannot implement that, right, or say function pointer, dynamic memory allocation, malloc, calloc, because you have to develop a hardware where you say that my RAM size is 100. You cannot say ki when I run first time I will make my RAM size 100, next time 1 lakh, you cannot do it, right. You have to take a decision that in this design my RAM size will be 100 and I want to use only 100 size RAM. But dynamic memory allocation, malloc, calloc exactly does the opposite. You run the first time, you can use 100, next time 1 lakh, right. So, you have to, those if you have malloc and calloc, that has to be replaced with a fixed size, that you know that for your application that the maximum size will be say 40. So, I will decide my size of the array will be 40. Okay. Or if you have a function recursive function, you can always write in a for loop, right, iterative. So, those are called make it synthesizable thing. So, whenever you convert anything with a automatic converter, you will have malloc calloc, you have recursive functions and all. So, somebody has to manually do this, replace all this malloc calloc with this fixed static size recursive function with this has to be done. Okay. Then if you look into this, as I mentioned that there are a lot of optimizations. You think about that your program has m line of code, okay, and there are n kind of such optimization possible. So, what is the number of possible way you can apply this optimization to this your code? M to the power n, right, because if there are m location, you can apply any of them here, right. If another location, you can apply any of them. So, it is m into m into m into n times, so m to the power n. So, these are the possibilities, right. So, somebody has to decide that I will apply this. So, that is not a easy process, but that is manual process here. HLS tool does not do that. If you do not ask him to do loop pipelining, it will not do loop pipelining, right. So, that is this part, that apply pragma based optimizations. The pragma is used to instruct the tool that you apply pipeline here. So, somebody has to do that hard task to apply the correct pragma, right. And also there are many source code optimizations are also there, which is basically I will talk about more, that whatever the C code, they may not be hardware friendly. Okay. You have to make the code hardware friendly. What is hardware friendly, by the way? Any idea what is hardware friendly? See, when you have say array access, right. So, when I write a code, I never thought about how many times I am reading the array elements. Probably I am reading the same array elements multiple times. Okay. But in hardware, whenever this map this array into say block RAM, every time you have to wait for one clock to get the value, right. So, if you read the value one value 5 times in your C program, you do not care, but if you read that same value 5 times, the same value 5 times, that means you waste 5 clock. Four of the clocks you could have saved, right. You read it once and store locally, right. So, that means I can rewrite my code such that I will not read any value from array multiple times, I will read only once, okay. And that version of the code is hardware friendly, because you are reducing the memory access, right. This is one of the example. So, that is what is called source code optimization. Again, these three is the manual effort. So, although it looks very good that you take your Python implementation, convert it into C, put it into HLS, it will give you the RTL, but these are the painful step you have to follow. Until you do it, you will not get your hardware. Okay. And specifically for say ML kind of model, where your line of code may be 10,000, 20,000, 50,000, this is not an easy job, right. It will take lot of time to make them synthesizable. Okay. So, this is where we are thinking LLM can assist, because LLM actually is a language model, right. So, if you tell him that you have this code and this is a recursive function, you convert into iterative function, probably if you have trained probably sufficient C programs, you will understand that, right, and it can do that. Or say you ask him to do the source code optimization, where you say you convert this loop into that. I will show you many examples. It actually can do very easily. You can check that it will do those kind of language processing thing very well. So, we leverage that facility of LLM into this flow, and this is basically LLM, right, and this is basically HLS. When I combine them, they actually make this process much easier, right, and that actually we have done, and we will show you some results how actually it is helping in developing good hardware from Python code or ML model quickly, okay. And we will show you that it is actually give you lot of optimizations. Okay. So, I will go through. So, I am not going to talk about what is large language model, everybody knows that, and it is being used everywhere. So, why not in this field also, right, I mean developing accelerator. So, and there are a lot of recent times interest in LLM, and there is a specific conference is happening nowadays, LLM aided design. How do you use LLM in your design flow so that you can do the design quickly, okay? And almost everybody involves, all the big companies are involved there, and it has a conference this time in Stanford University, right. So, a lot of interest in the community to use the features of LLM in the VLSI design flow or the design flow, right. One recent research is happening where people saying that why I need HLS, I do not want HLS, I will say ki this is my C code, give me the Verilog. LLM understand this, right. So, why I need the HLS, I will replace HLS with LLM, right. There is a recent work is happening. So, where basically it is kind of a chatbot, right. There are quite few are like chat EDA, chat pattern, chat Nemo, where basically you give the specification maybe C code, and using this LLM and agent in loops, probably it will not give you correct Verilog at the first go. Then you tell that these are the mistake, and that mistake also you can identify, you will just running in your GCC, right, and you see this or say this some Verilog simulator, and you say okay, these are the syntax error. You identify, and that LLM again was prompted that you correct this mistake for me, right, and with multiple iteration it will correct and give you the Verilog, right. That is the kind of things are happening, and there are quite few such work, right. Verilog, that GIAN, which is very recent work, then this is Verilog generator, right. So, you see here you have basically they just train the model with lot of Verilog code, maybe all GitHub of Verilog, right. So, and then they train the model and then they try to do this, right. So, there are so many work. So, I am not going to detail of them. Then AI Verilog generation, then there are zero shot RTL code generation from specification using large language model. So, there are quite few interest in this domain. Now, the question is then do we need a HLS, right, that is the question. So, if LLM can give you the Verilog, then I do not need HLS, right, I do not need HLS, I just use LLM, right. So, is there any value of HLS, right. So, that study we try to do, and then we figure it out what is happening in this community, and this is the kind of design the current LLM can generate correctly, which is basically just simple 2 input multiplexer, 3 input priority encoder, half adder, FSM with 2 states, right, truth table of 8 bits and so on. So, these are very small design, right. So, although LLM can generate correct Verilog code, you do not need to write Verilog code, it will give you, but the design size is quite small, right. So, whereas if you consider the ML models, we have considered 6 ML model in our experiment, the code size is 4,000, 10,000, 1,48,000 and so on, right. This is the kind of model size, this many layers. So, it has basically 8 layers, first layer has 640 neurons, this has 18,460 neurons and so on, right. So, this is the size of your, these are also small model, these are not the big models, they are very small models. So, the size of your design is too big, and LLM is not something can adopt or handle such big specification and give you Verilog code, right. So, it is basically the takeaway of the discussion is that I do not want to replace HLS with LLM, rather LLM will improve the HLS based RTL code generation process, right. The way I talked about that you take those manual effort and use LLM there, okay. So, that will help. So, I will give you basically this will become now LLM. So, then this process is easy, you do not need to break your head there, right. So, it is basically LLM will make all these things done for you, and then HLS will give you the Verilog code. That is the viable approach, okay.
So, this why LLM can design small designs, and what is the bottleneck here that it cannot design these large things?
Yeah. So, first of all, as you discuss in high level synthesis, a lot of decision is making is there, right. So, how many clocks is there, how many clock cycle you need to execute, how many register is needed, how many multiplier is needed. So, that decision LLM cannot take, right. It is basically a language converter, it try to do a one-to-one mapping of the instruction kind of. So, whenever those kind of complex decision has to be taken, and LLM is not aware of them, right, and it will just mixed up. So, that is why if you just see here, these designs are only very few lines of code, right, maybe 10, 15 lines of code, right. So, it is not that efficient.
So, is it a question, so then it is a good path to take?
Which one?
So,
So, if you ask me, it is not a good path to take. So, because high level synthesis has lot of design decisions, and that is why I spent almost 10 minutes on scheduling, allocation, binding. I know that is little bit extra for me, but just to emphasize that high level synthesis is not just a trivial process, lot of decision is happening there, and unless you understand the decision, I mean so many decision steps, you will not appreciate that HLS is far better than LLM, right, in generating Verilog code from C. Understood? Okay. So, we have taken this and then we do this funny experiment, right. This is done by my students. So, what he did is effectively the first step that makes sure that synthesizability. So, we identify these are the primary issues when you generate a C code from Python, that you had dynamic memory usage, system calls pointer, function pointer, recursive function. So, what we do is basically we run it in high level synthesis and it will give you this, these are not supported, those error message we give it to LLM, right. So, we do not identify anything manually, we just give the code to HLS, it will say no, I will not able to handle your line number 50, line number 71, line number 32, because there is a memo malloc is there, there is a system call there. So, all these things will your HLS will give me, right. Then what will do, there will be another LLM that will parse that and identify all this error and create the prompt and give it to LLM, and then based on that LLM will correct those things, right. It is a repetitive process, you cannot just get everything in one go, maybe 10-15 iterations. This will give you the code which is synthesizable, at least there is no such thing which is not supported by the HLS tool, right. This is what I have done and it actually does very well. You have to just give you some instruction earlier that if you this code you convert into this. So, you have to basically play with the LLM to tell him that the dynamic, if you have malloc you write the code into like this and so on, right. So, then he will understand. Then as I mentioned, these are the kind of examples. Say for example, if you have a dynamic memory allocation, then you replace with a static memory allocation. If you have a function pointer, you replace with a fixed pointer and so on, right. If you have a recursive function here, you convert into a for loop, right. So, this is LLM will do for you. Okay. Then LLM for source optimization, this is something I want to spend little bit of time. So, as I mentioned, what are the things, how to make your code hardware friendly, right. So, there are many source code optimization, one of them is loop merging. Say for example, you have four for loops here, right, 1 for loop, 2 for loops, 3 for loop and 4 for loops. So, you can do one, I can combine these two and I can write one for loop for this, right. This is what basically happening here. Then what will happen, this operation and this operation will happen within one loop. Then there is a possibility of parallelism, right, I can execute both of the operation parallelly, right. So, then if it take n clock cycle, it will take 2 n clock cycle, but if I do it parallelly, probably you can do everything in n clock cycle. So, this is what I am talking about, the hardware friendliness, right. Instead of having too many loops, you can merge similar kind of loops together, so that you can run the body of the code parallelly and it will improve your clock cycle, right. So, this is what one of the code optimization. So, again if you just give this prompt and you give this code and this is generated by LLM. So, it will basically identify and it will actually identify that you cannot merge this with this, there is a data dependency, okay, or you cannot merge this with this, at least this kind of things it identifies, only whatever mergeable it merges, right. This is exactly generated by LLM, not by us. Similarly, loop interchange is another thing. So, for example, you have everybody know matrix multiplication, right, everybody have written the matrix multiplication code, right. So, there are basically 3 for loop, right, I, j, k, right. So, if you have the first for loop is I, then second for loop is j, then third for loop is k, and effectively what happened, there are 2 matrix, right. You take one of the row, you take the column and then multiply element wise, right. So, this k actually go element wise and this basically this I select the row, this k select the column, right. And then this sorry, I select the row, j select the, this is your I, this is your j and k selects the elements, right. So, if you have this I j k and you just convert into k j I. So, you basically bring this loop here, only the order in which the operation getting executed will change, right. So, your final output will be same, but intermediate value may be different, right. But this Kij is much more hardware friendly, because the locality of reference is increased, right. You are not going to read one value or multiple, you are not going to read one value. In this you are going to read the same value n times, but here if you write k and j, Kij, you are going to read once and reuse more. You can do that, you can go and check detail, but that actually happen, right. So, just converting in your ij key into Kij make your code hardware friendly, right. So, that is called loop interchange, right. So, similarly you have loop tiling, this is another very interesting. So, the systolic array architecture Professor Mishra was talking about yesterday. So, here basically this is your that one box of module, right. So, effectively you have ijk, you are basically doing for entire thing, right. So, you are computing for entire thing. What you do, you create a tile of small tile, right, and this ij key is basically this tile. So, you compute, so you are supposed to do something from this to this, right. So, now I will do the same thing only for this part of the code, part of the data, right. I will do the same thing for this part of the data and this part of the data, and this I can do parallelly. That is what is the systolic array architecture, you can take advantage of that. So, what is happening here, you have j and k, you have still this ijk, but it has become 6 nested loop now. This is the one block, right, it is happening for say kk times, right, and now this loop will be incremented by tile size. So, you are basically you take this, perform this operation, then you go to this one and you perform the same thing, right. So, this is what is basically tiling, and this is actually is very important optimization for making your code parallelize, right. You can actually run this all module in parallel if you apply certain optimizations. So, these are the thing LLM can do you. If you just give this code and apply this, you give this instruction, it will give you this code. Okay. Similarly, as I mentioned, there are pragmas, pipeline, unroll and all. So, you can actually apply them. So, if you give this code and if you give this prompt, it will add pipeline here, unroll here, and this is actually a good decision, okay. Because if you unroll this, that means it will basically flatten, right. You need lot of areas, lot of units, and then you pipeline here. Whereas, if you unroll here, then entire thing will unroll, this 2 nested loop will unroll. So, you need basically n square area. Here earlier if you need one area, if you unroll the inner loop, it will need n area. If you unroll both of the loop, it will need n square area, right. So, what they are doing actually intelligently, that it actually unroll the innermost loop. So, that you need, instead of one area, now it is 1 unit of function unit, you need n unit of function unit, but then you pipeline the entire module, right. So, this is a good decision, and this is basically done by LLM with this prompt, right. So, this is the kind of design decisions. So, effectively this is our flow, which is we have given the name LHS, which is LLM assisted HLS, right. This is specifically for ML model. So, you have the CNN model, you have this Keras to C, which can convert the Python model into C code. So, this is the C code, and then I use the LLM to correct my synthesis error. So, I give the LLM to correct it, and then I do the HLS, and if there are some error, I go back and then correct it, right. So, if there are synthesis not successful, go back, identify what are the problem, give it to HLS and go back. So, after some loop, I will get the synthesizable code, right. And then I use this LLM to identify all these source code optimizations, then I get the source of code optimized code, then I use LLM to insert the pragmas. I got some pragma inserted code, then I do the HLS, I get the RTL, I check whether this my target, let is that I want to first of all I want to fit this design into this board, right. If you can fit it there, I am done, that is my objective, right. And when I fit, I try to optimize the latency. So, I want to make sure that it is kind of resource constant latency optimization, that I want to make sure that this design must be fit into this FPGA board, and then you optimize the latency for that. Okay. So, this is what happening, and this is the detail of the model which you can skip. We have used this Vivado HLS high level synthesis tool, ChatGPT 4 for the LLM. Okay. So, interestingly you see that the number of prompts are not high, right. So, for source code optimization we need only 4 or 5 prompts, right, but the same thing will applicable to many snippets, the same kind of code, right. So, this is the showing that number of prompts I am using, and interesting, the number of prompts are actually quite less. You can actually easily convert them into so this is for source code modifications and all. So, it do not take much time to convert them into synthesizable code. Okay. And similarly, this is for optimization, right. So, it is basically for number of prompts. Here the prompt is bit high from the first one. So, then in the first task of the making the code synthesizable, LLM is quite good doing that, because this is a very mechanical work, right, and LLM is going good in doing that, and this is the some results for that. And then what we did is basically so that the improvements, say for example, you see this is the design, the baseline latency was this much. So, this many clock cycle, you can see it is kind of some crore, right. This many cycle is needed to give the output if you do not apply any optimization. And then once we did this with say everything source code and pragma based optimization, this is the latency I got, and the improvement is 26 times, right. So, I am able to improve the latency by 26x. For the same next design, we are able to reduce the latency by 2690 times, right. If earlier it is 2690, it become 1 now. So, this is the kind of latency optimization we are able to achieve through LLM. We have not done anything, right. So, we have just used LLM to apply this pragmas, apply the source code optimizations, and this is the kind of improvement we are able to get through LLM, right. So, that is something interesting, right. So, LLM can help you. So, there is one more tool called HLS for ML that also does the similar stuff, that if you take a ML model, it will give you the Verilog code, and what we found that it was quite difficult to generate a Verilog which can fit in a target board, right. So, either it will optimize the latency and give you a design which has too much of area, it cannot fit into any board, or it will give you a design which has very less area, but the latency is too high that it cannot be useful, right. So, that is the problem with HLS for ML, and it is very difficult to play with that. There is an option called reuse factor, but that also very hard to apply. Okay. So, it is basically when we try to do that, we are able to see that at least for 2 design we will not able to do the synthesis at all, right. So, whatever pragma they are inserting, that HLS tool is not able to synthesize the thing. And among these 6 design, in 4 cases our this LHS work, which is LLM based optimization, actually beats HLS for ML, right, in terms of the overall performance, right. So, here you can see that our performance is, we are able to improve it is by 10,000, it is 6,000, right. So, it is 49 here, our case 52 and so on. Some cases they beat us, 2 cases, but this is an automated platform, right. We are not doing any optimizations on our hand, right, everything is LLM is doing, right. We are only using LLM to optimize the design. So, so that is something is interesting, right. And in future actually some part of the things is still manual, in the sense we can this whenever there is a synthesis error, at this moment we just extract the error and give it to LLM, but that also can be done by another LLM agent, right. So, that is the enhancement we can do, then the entire process will be completely automated. So, this part is manual at this point, but which can be trivial extension. Okay. So, that is all for this session. So, in summary, LLM can actually be utilized in the HLS flow to create efficient ML accelerator, right, and it has been demonstrated with this work. Okay. So, thank you. So, we are done for this session, we will have half an hour break, we will come back after 30 minutes at 4. Okay. Okay. Okay, so let us start again. So, in this session we are going to discuss about the security concerns of machine learning hardware. Okay, so, once you implement this, it is good that you can create efficient hardware running on edge IoT devices, but it have some security concern as well. Okay. So, I will primarily cover various attack first. I mean, what are the kind of attack possible on the machine learning hardware, and then I will talk about the kind of protection techniques. This attack on this machine learning model is something is not myth, right? It is kind of reality, right? So, you can actually see lot of news. It's, I mean, some of the news may be 4 years, 5 years old also, right? There are side channel attack target machine learning models, right? So, security in critical at the intersection of AI and 5G. Then you have say that this says that defending AI system from cyber attack has not been solved. So, these concerns are real, and there are already reported issues that people try to attack the ML models, right. So, if you try to categorize your all attacks, it is basically primarily I am talking about privacy attacks. So, you have this membership attack, membership inference attack, reconstruction attack, model extraction attack, and property inference attack. So, these are the 4 different kind of attacks possible. I will primarily focus on this model extraction attack, and then if you see the model extraction attack, it is basically as the name suggests, it is basically you are extracting the model, right. So, basically what is the motivation here in this model extraction attack and all? See this when you try to run this ML, how do you get this ML model, the trend model? Can you tell me what are the steps you have to do to get this training process done? What are the things you need?
Data, firstly data processing steps are there, sir. After that data splitting steps, tokenization parts are there.
Yes, yes.
And thereafter, sir, we go in for the training part.
Exactly.
Iteration of epochs are carried out.
And you need hardware GPUs, right. So, as your friend mentioned, so you need data, and data is not free in this world, right. So, it is basically costly. So, availability of data is a concern, sometime it is not available to you, right. It may be sensitive data, say some patient information that that the hospital does not want to share with anybody, right. So, the data is first of all not available all the time, or it may be costly. If something is available, you have to buy with cost. And then there are a lot of data processing, as your friend mentioned, that also involve time and efforts, right. And then the training, and training needs a very costly GPUs, right. You have to pay money, either you purchase in maybe $35,000, $50,000 what Professor Mishra was saying, and purchase your own GPU, or you pay the cloud provider and use that. So, it is all involve cost, right. And then through entire process, what you effectively get, if you just think about the deep learning model or neural network models, what effectively you get? What is the trend model?
They are weights to it, sir.
Exactly. So, you kind of know that there are 10 layers, each layer has 4 nodes, 10 nodes and all. So, you know the kind of structure, how many nodes, it is kind of known to you. Only thing is through this training process, what it does, it goes those exact value of those weights, right, and biases. So, all the cost involved there is to get those values, right. Now, if somebody do some attack, right, you can think about this weights are now the cryptographic keys, right. Whatever the attack you have done for this AES key finding, I can do the same stuff on the ML model, and I can identify the weights. So, then I do not need the data, I do not need to pay for my data, I do not need to pay for my GPUs, I do not need any manpower to do the training or data processing, right. So, that is the kind of motivation of the attacker to attack the ML models, understood, right. So, this kind of model extraction attack. In model extraction attack, you have kind of 2 kind of categories. One is basically you exactly identify the weight and biases. It can be basically other like hyperparameters, then architecture, train parameters, but primarily we will look into this, which is basically the weight and biases. An approximate model is basically you do not need to get the exact weight and biases, but somehow you kind of create another model which will behave similar, right. So, something like this. So, once you think about, and I am talking about attacking the ML model on the edge and IoT devices, and it can be done through software or you can actually do through hardware, right. So, I am mostly focused on this. So, this is my kind of line of discussion, right. So, once you think about that ML hardware which is running on ML this in a edge or IoT devices, you can again do the side channel attack, which I spent time in the first half talked about that, or you can also do the scan chain attack. I will talk about both, right. So, in this kind of talk I will briefly talk about the other attacks. I will not go into detail of them, how it is being done and all, but I am primarily focused on this, and this is basically the most important one, and in that also I will primarily talk about when it is being run on a devices like IoT and edge, how this attack is possible, right. This is the kind of plan for the talk. Okay. Any questions here? Understood? This is the protection I will talk about later. So, the first one I was talking about is membership inference attack, right. This is something interesting. So, it is basically try to see that where a particular data was used in the training process or not, right. So, you have some data, say for example, you want to check whether that particular industry use your data, your medical data, right, whether you have used their all your whatever the reports you have done, all the data is with the company, whether you just want to check whether they have used your data or not, right. So, that is inference attack. So, in some cases suppose you have not given the permission that you do not use my data for your training purposes, but still they have used, right. How do you guarantee that they have not used, right. So, it is basically membership inference attack is that it is basically attacker prediction vector, and it is basically clinical record was used for train a model or not, right. So, this is whether they have violated the kind of agreement, right. In general, this is the kind of architecture for that. What you did that you have the model which is running in some say IoT devices or cloud everywhere, right. It is a black box to you. You do not know any information about that. What you do, you can actually query with your any data, right. You can always do the inference, and that is what is called shadow. You get some prediction also, right, for that data, that this. So, what it does is basically think about that you have some say some test report, you say whether there is a cancerous things or it is a benign, right. So, some such kind of things, or you have thyroids or not, so something like this, right. So, you have those data and it will give you the kind of predictions, right. So, you can take that model running on IoT devices or edge devices or in cloud, you create set of data set, you can run for 10,000 cases, right, who stops you, and you create data set, right, you create some k data set and you break it into training set and test set, right, 80-20, 90-10 whatever it is, and you create some shadow model, right, on this data set, because this is your data set now. And then you have this k such shadow models, and then you basically say if it is part of this you just add this output in the data, you augment with this data set in and out. If it is part of the your training, then it is basically in, if it is not part of the training, then you say out, right. This is how you basically augment this in and out your data set, and this entire thing you use for train another ML model. This is your attack model, right. So, what you will basically do this, it will now predict whether a data was in or out of a so, if you give any data now in this model, it will your output will be the classification in and out, right. So, whether that particular data was used in your training process or not, right. So, then you take this attack model, you now take this some data, you give it to this cloud or IoT devices, it will give you the prediction, you add this level and this, and it will give you whether it is part of training data set or not, right. This is the kind of model you can create, and which you can with that you can actually check whether this particular data part of this target model or not, right. This is the kind of overview of this membership inference attack. Okay. You can also have reconstruction attack, which is basically suppose you have a blurred picture, right. So, you have basically a blurred picture, you do not have the exact picture, you try to reconstruct back the original picture. Say for example, you do not have the original data, you want to convert into the correct the recovered actual images, right. So, it is basically use generative adversarial network, where they use this blurred data and create this model and try to get the recovered data, right. This is another kind of attack, reconstruction attack, where you reconstruct the original image from a blurred image. Understood? You can also have this property inference attack, which is another interesting attack, which is basically happening during federated learning, federated mode of training process. Say you have one server, you want to create the ML model, but you do not have the data with you. What you do in that time, right? So, you do not have data with you, but you want to create the model, but the data with somebody else, right. So, suppose this guy has some data, this guy has some data, and this guy also have some data, right. So, what you basically decided that I will create the model structure, I will give it to this guy, he will train on his data and he will give you the trained model to you. Everybody basically take the model, train it here and give you back the trained model, right, and you combine them together, right. So, you get model from model 1 from here, model 2 from here, model 3, and there is a kind of, there are many ways you can aggregate these models. It is kind of combine the weights, right, and maybe take an average of the weights to get the combined model. So, this is kind of very well known structure, where you don't own the data, but you still want to create the model, right. So, this is kind of federated learning model. So, these people does not want to give you the data, but he is agreed to you that I can train the model on my data and can give the trained model, right. So, he basically still can say protect his data, but still the training process can happen, right. So, now in here in this kind of federated learning process, somebody is adversary, the attacker, right. He also say ki, oh, I will also help you in this process of training, right. But his objective is something to get some other information from the others data, right. So, that is the kind of his objective, he will help you see what he is getting. So, he is getting, say suppose this process is happening for say 20 iterations. So, every iteration he is getting a trained model, and that trained model has some impact of the data of this guy and this guy, right, other participant, and he can actually compare the first version, second version, third version and all, right. So, he has all these version with him, and he can actually do some kind of analysis on that models, different versions of the model, and from there he can actually identify certain property about the data of this, right. To give some example, that say suppose you try to create the model to identify the gender of an image, right. I give you an image, you will say it is male, if I give her image, you will say it is a female and so on, right. But this guy want to see whether they are using the glasses or not. Suppose this is a company who want to sell spectacle, right. So, they try to identify how many of the data, this may be this company's total data. So, the employees, he identify how many people want to is wearing glasses there, so that they can connect these people and try to sell the maybe spectacle to them, right. So, this is the kind of an example, that although the final model is creating for say gender decision, that whether a particular image is of a male or female, he try to create a model that will also identify whether a particular person is wearing glasses or not, right. This is the kind of property inference attack in a federated learning mode. Any question here? Okay. So, these are the other possibilities, but as I mentioned, my objective is to give more detail into this model extraction attack, where I want to get either some hyperparameters like what is the batch size optimization algorithm being used, or the architecture means number of layers, layer type, or the what is kind of kernel is used. But the most popular one is the trained parameter, that basically the weights and biases of the neural network, right. This is the kind of more important attack. Okay. So, this something that I have already explained. So, basically this neural network has all these different layers, and each layer has neurons, and it is basically if it is a fully connected, this value will go here, this value will go here, this value will go here, and every this edge has some weight, right. This is maybe W11, this is W12, this is W13, and suppose this is the value x1, right, this is x2, this is x3. So, basically it is happening xi into wi summation in this node, and then you are doing some activation function, it may be ReLU or other kind of activation, and then you will give the output, right. So, this is what is happening in each node, right, this is everybody knows. So, through the train process this value of this W11, W12 these things has been decided. So, extraction attack try to get these values, right, these weights. Okay. So, that I have already explained. Either it can be done with side channel or scan chain. So, side channel attack I have already talked about the power side channel. So, again I will show you how power side channel attack is possible on neural network hardware. Okay. I will give you walk through that process, and then I will talk about some countermeasures. So, this is the diagram I have shown earlier also, that basically you have some cryptographic devices running there, you can control the inputs and you can control see the waveforms power, you get the power, and from this analysis of the power you can actually see the cryptographic keys, right. So, in the neural network framework instead of the cryptographic keys here you are actually the neural model is running, right, that is the difference. And you can do the same process, you can control the inputs, you can control the inputs, and you can actually get the power, and you can correlate and you can get the weights. Okay. So, that is all, this is more detail. So, before going into the attack, in general in IoT or edge devices I already talked about the quantization, right. So, once you make your weights basically binary, then it is basically called binarized neural network or BNN, right. So, effectively you have this value W1 is basically 1 or 0, 1 means you multiply and the other is you do minus 1, right. So, either you sum or subtract, okay. And this is basically to reduce the weight, right. So, it is basically in each node you are doing Wi xi, your all inputs are coming from the previous node and you are multiply with Wi and xi, but your value of the Wi is basically either 1 or 0, and 1 means you add and 0 means subtract, right, that is what is happening. And then this activation function is ReLU, it is basically if the summation is 0, if it is less than 0 then the output will be 0, or it is greater than 0 the value will be 1, right, this is what the ReLU does. And then finally, you have the max pooling function, which will just calculate the max of all these values, and that will give you the classification, right. Understood? This everybody understood, only difference with the neural network is that this Wi, the weights are basically binary here, and what is my objective? I want to get this value of Wi in the entire network, right, that is my objective. Any questions so far? Understood? So, how do you implement this node effectively this neural network? It is effectively summing these values, right, all these values Wi xi, right, W is either plus 1 or minus 1, I basically sum or subtract. So, you can actually create a adder tree, right. So, if you think about that there are 784 inputs. So, you have these inputs and you basically do the summation of two values, there will be 784 by 2 number of adder in the first layer, and you will get 396 values that you store in some register. Then you will have half of 3 for 96 adder in this, you will get 196 values and so on. Everybody understand this implementation? Anybody who do not understand this, how this actually the behavior of the node will be implemented in this node, this adder tree? Everybody able to follow this? Yes? Okay. So, this is quite straightforward, right. You basically have a pipeline design, you have one level of register here, you do the first level of summation, then the second level, and the final sum will come here, right. And where the attack will be mounted? These registers, right, these registers. Whatever the register, I try to see the power consumptions on a particular register, so that I can identify what is, because this value is what Wi into xi, right. So, either it I know xi because xi I am giving, you do not know whether it is getting adding or subtracted, right, that is what you want to know. So, I can actually observe the power here and then I can figure it out whether it is these two value getting added or subtracted, right. Only thing is that I do not have access to this value. If I have the access to the value, I can directly tell whether this is addition or subtraction, right. To give you more idea is if you access to these values, say suppose you are giving here 5 and 3, right. If this weight is say I know this weight, so this is minus 3 say plus 3, so the value will be 2, right. So, if I get the value 2 here, I will definitely know that the W1 is minus 1 and W it is basically 0, that is why it is minus 1, and W2 is basically 1, that is why it is happening. So, if you have access to this value, the attack is straightforward, right. But in the power side channel, as you mentioned, that we do not have access to the value, but I can measure the power at this point say. So, what I will do? I will effectively do it for multiple time, right, and then I will see what is the change in power, right, what is the Hamming distance between the power. So, if you so as I mentioned that if you have this value is get summation, then the weights are 1 1, because if it is 5 plus 3 say, then it is 8, right. So, but if it is say 1 0, then it will be subtracted and so on. This you understood, right, based on the values that I already told you. So, it is very straightforward if you have the access to the values, but unfortunately you do not have access. So, what attacker will do? It will not run for only one cycle, it will run one cycle, it will observe the power, then second cycle will observe the power here, third cycle observe the power here, and if it is say getting summation, this will always follow the same pattern in this node, right, if it is say both are getting added. So, what I can do? I can see the Hamming distance between these two value, and usually Hamming distance is basically, you know what is Hamming distance? Is if you have two number, how many bit they differ, right. So, if it is say 1 0 1 0 and this is 1 0 0 0, what is the Hamming distance? 1, right, only one bit it differs, right. So, effectively and this is the toggle happen here, right. So, basically why I am calculating the Hamming distance, the power consumption as I mentioned earlier, how many time your value goes from 0 to 1 or 1 to 0. So, the power consumption is proportional to the Hamming distance, right. So, I can measure the power here, and based on the this power consumption, I can actually guess what is the Hamming distance between these values, and from there I can get the power. You got the idea, right? Do I need to clarify this again? Understood? Okay. So, this is how the attack will happen, and as deep you go, it will be much difficult. So, you will basically do this attack here first, then you will do the attack in this next layer and so on. This is how we are going to do that, so that you will be able to get all the weights. Okay. So, so that's basically the basic idea. So, this is how things being done. Now, solution is the masking, right. So, we have already discussed masking. So, we are going to implement masking on neural network, and we are going to use arithmetic masking, because your inputs may be integer, right, it is not binary masking. So, as I talked in the first half, that if you have arithmetic masking, so if you have a value x and if you want to create 3 shares, I am going to use 2 random R0 and R1, and my shares will be x minus R0, then R1 and R0 minus R1. This is my x0, this is x1 and this is x2. And the same convention, if you have access to the 2 value, you will not get the output. When you have access to the all values, you will get x, right. So, if you assume that I cannot access more than 2 location, then this particular solution will give you I mean it will protect your model from power side channel attack, right. So, if you can correlate the masking thing that I have talked about in the first half, this is straightforward, right. So, basically what I am going to do, I am going to break my weights into shares, and I am going to implement the entire things with shares, right. So, I can assume that I will basically have say 2 shares. Okay. So, then this is one adder tree, I will do. So, if you have 2 shares, then what will happen? It is basically, if you have 2 shares, you will have x minus r 0 and r 0, right. So, you have one share is x minus r 0, this is share 1 and the other one is r 0. So, then I will do the entire thing for x minus r 0, the entire thing I will do for r 0, 2 shares, right. So, I will basically have 2 copies of the hardware, right. And then this is yeah. So, this is the original one and this is now break into 2 shares. Okay. So, basically you have kind of 2 copies of the adder tree because you have 2 shares, but there are few more interesting things happen here which I do not want to go that detail, but it basically says that if your value of this it basically says that if A is positive, A is that x I was talking about, then A minus r value is the chance of being A minus r become 50%, right. And if it is A is negative, A minus r will chance of becoming positive is 75%. The calculation I am skipping, but you can actually, it is very simple actually. So, suppose if this also positive, this also positive, right. So, and you are doing say A minus r, right, then there is a 50-50 chance, right. If A greater than r, then it will be positive, if it is not, then this, right. But if this is positive and this is negative and you are doing A minus r, this is definitely a negative number, right. So, this way you can calculate in which case what is the chance of the result is positive, negative, and you can take an average, this is 75%, this is 25%. So, what is a nutshell that from the probability of the value being positive or negative, I can actually make out whether the A was positive or negative, right. So, it is basically leaking information. So, that means sign bit actually getting leaked, right. So, effectively what is being done here, you calculate this sign bit separately, right. So, you do this adder tree for only the data, sign bit you calculate separately, okay. That is the idea securely. And then you remember that I am doing this summation because you need to combine these values. So, you again create a randomized version, here I am basically using LUT based implementation, I am not going into detail again, but this is kind of a safe or secure carry carry propagation implementation. So, that I can check whether the value is greater than or less than 0, right. So, this is basically for activation function ReLU, you have to check whether x greater than 0 or not, right. So, that can be done with this, okay. And then finally, you have to do the max pooling. In the max pooling you have to take a max of these values, right. So, you have to compare 2 values, but I cannot combine these 2 shares, right. If you combine, then the value will be leaked, right. So, what I will do, I will not check this greater than this one or not, right. So, I will do what, I will just swap these values into this, so that I am not combining the share. Did you understand why the combining is a problem? If you combine these 2 share, the result will be A, and that is the secret to me, right. So, if you add these 2 share, then you will get A, but I do not want to do that. So, what I will do, I will not add them, rather I will just bring this here and I will bring that there. So, it is basically no summation, it is basically combine the shares of 2 different values. So, they will not reveal the data. So, this is basically a detailed discussion how you can actually implement masking on machine learning model, which is quite different from what I discussed in the first talk, right, where I talked about how we implement masking on cryptographic design, right. So, here to summarize, you need to implement this sign bit separately in the summations, because that is revealing something. For max pooling, you do not do the summation, then it will reveal A, rather you do this strategy. And for ReLU, you have this ripple carry thing, which actually can check whether x greater than 0. So, these are the detail of this implementation, through which you can create a masked version of machine learning model. Understood? So, that will be a safe solution, okay, where people cannot do the power side sensor attack to get the keys. Understood? Again, this is a future direction where I talked about that this masking has a lot of overhead. So, why not the transpose things, the circuit transformation I talked about, we can also implement the same thing in in machine learning model as well. So, that will have a less overhead as compared to the masking. Okay. So, that is a possibility. Everybody understand this, right? Okay. So, this side channel thing is done. Then I will talk about the scan chain attack on neural networks. Anybody know what is scan chain? Professor Mishra talked about this yesterday. What is scan chain?
So during manufacturing, that time the scan chain is utilized to find out whether there are errors or not.
Yes, exactly. So, it is basically to use for identifying manufacturing defect. So, if you have a circuit of say 1,000,000 transistors, if somewhere there is a manufacturing defect, as sir mentioned that there is a disjoint or there is a cross connection between two wires and all, your output won't come correctly, right. So, how do you identify or localize those things that there is a manufacturing defect, you have to test it, right. So, to test it you need to get access of the internal data. So, which is not possible in the actual chip, because you only give input, you have the output. So, what test community come up with this scan chain, right. In the scan chain what happened, whatever the register you have in your design, so their actual input is coming from the circuit, right. So, this is they say this is the circuit that is updating this register, right. For each register there are some circuit that is updating this register. But what I did, I just add a mux here and I connect one scan input in, scan in, and I put a mux here. This is the original input of this register, and this is the previous register input here, right. And this is basically scan enable, right. So, this is 0, this is 1, and for each circuit, for each register I did the same thing, that I just connect the original thing into 0 and previous register as 1 to this multiplexer, right. Then what will happen, whenever you give this scan enable equal to 0, what will happen? If I give scan enable to 0, what will happen? It will take the input from the circuit, because this will be 0 and this value will come here. So, this scan chain is disabled basically, right. That is called functional mode, where I give scan enable equal to 0, so that whatever the circuit interconnection, that will work. Understood? On the other hand, if I give scan enable equal to 1, then what will happen? Which value will be selected here? This one, right. That means whatever the outside value are giving, that value is going to store in this register, right. What will happen for this register? Whatever this output, that will go here, right. What will happen to this register? This value will go here, because this is 1. So, if I run it for 1 clock, what will happen? Whatever the input I will give, that will come here, right, and others will get some arbitrary values. So, to populate this register with my values, what I should do? So, suppose I want to set here 1, 0 and 0 here. So, I want to set this so that I can check what is happening in this circuit, because if I know this is 1, I know this is a OR gate, I can see what should be the expected output, right. So, if I run it for 1 clock, I will give 0 here and that 0 will store here, right. Next clock I will make it again 1, I will give 0 again. Then what will happen? This 0 will move here and this 0 will come here, right. So, you will have 0, this is also 0 and this have some arbitrary value. Next clock I will give 1, then what will happen? This 1 will come here, this 0 will move here, this 0 will move here. So, in 3 clocks I can set whatever value I want to set to this registers externally, right. This is the purpose of scan chain. Now, see this, what is the, say suppose now this sorry, I will just take about this. So, this is say NAND gate, right. Maybe I will clear it little bit. So, in 3 clock I disable the circuit and I set the value 100 to this register, right. Now, I want to check whether this is actually a NAND gate or not, right. So, say suppose I give here 00, this output is 0 and say this value is 1, right. So, this 1 will come here. So, what will be the output of an AND gate whenever it is 1 0? It will be NAND gate, it is opposite of AND, right. It will be 1. So, then this 1 should come here, right. So, what I am going to do is I know this value is 1. So, and this value is 0. So, this value should be 1, right. So, for 3 clock I make this scan enable equal to 1. So, that I set the value 1001. Next clock, 4th clock, I will do this scan enable equal to 0. Then what will happen? This value will now store here. It will erase whatever the value I write. But I know that because I know this structure, this value must be 1, right. So, whenever you put scan enable 0, now this will not take from the previous register, it will take from the circuit. So, now say this value becomes say 0, this value becomes 0, this value becomes say 1 because of these values, right. Next 3 clocks, this is basically 3 clocks, this is 4th clock, this is say 1 to 3 clocks, right. This is 4th clock, then again 5 to 7 clock. I will make this scan enable equal to again 1. Then what will happen? This value will go out from here, right. So, I will get first this 1, then I will get this 0, then I will get this 0. So, whatever value it was stored there, that will come out. Now, I can check that since this was a NAND gate here and I give value 0 0 here, this should be 1, but I got 1, right. It should be 1, but I got 0. When you get this value out from your scan chain, you can actually cross check what was the expected value and what you obtain. If they match, that means what? This was an AND gate, right. But if you got 0, that means the way this NAND gate is implemented in your circuit, there is some fault there. You will say that there are some fault in your chip, and in that is how you implement the NAND gate there. Did you get my point? How this scan chain actually help you to go internal detail of your circuit, and this is the kind of sequence of value which you can give scan input equal to 1 or scan 1 or 0. You got the point, right? So, this is basically scan chain, and it is being automatically inserted in any design by any software, right, because you have to test your chip. Okay. Now, in a machine learning model, when you implement, usually the output of this neuron gets stored in the registers, right. So, the output of this neuron where you are doing Wi into Xi plus checking the ReLU, that output goes stored in the registers. Okay. Now, when you do, if you send your chip to the testing facility and there may be some not dishonest people there, they can utilize it, this scan chain, and whatever I explained here using this same procedure, they will get the output of this node, right. So, they can exactly get the value what is output of each neuron, right, through the access of scan chain. Did you understand this? Yes, that because this scan chain have to added to this, I mean this register will need to be there for say probably you add a latency layer here. So, there will be register there, and this register will be connected in scan chain for testing purposes, and the dishonest person utilize this and you will get this output. When you get this output, can you get W? Because you can control X, right, you are doing W in I into Xi. So, if you give say it can be binary or any network, say suppose you give X equal to 5 and your output you get 20, can you make what is W? What will be W? It is 4, basically it is Wi into Xi, right. So, same philosophy, what he will do, he will give all other values 0, only one value is some non-zero, and then it will basically get W1, because in that time only W1 will be stored there, other is multiple, see especially Wi into Xi, right. If you give Wi equal to Xi equal to 0, it is becomes 0, only one value is non-zero. So, this guy what will do, if there are 10 inputs, it put all 9 inputs 0, one value 1 and non-zero, maybe 1, 5 whatever it is, and it will get the value. From there he can make out what is the Wi, and he will do for each input. First it will give this value is non-zero, other 0, then it will give the second value non-zero, other 0, and this way he using scan chain he can actually get all the weights of your design, right. This is the scan chain attack. Okay. So, this is basically have detailed basically if suppose you want to attacking this node, we have example here. So, you give such a way that only this value is say non-zero, other are 0, right. So, you will get this value effectively. Then I make little bit value modification, because there is a ReLU operations, it is not the exactly WIYI, because there is some bias getting added, right. So, what I will do, I will now give say suppose I initially I give x, right. So, I give C1 as x, and then I will give Ci plus some value Ci plus 5, okay. And then you make a difference between these two, you will get exactly the difference, all this bias everything goes out and you will get the weights, right. So, in 2 iteration you can get that. Everybody understand this? The same thing I can do for other layer, but if you go further layer you have to do little bit more calculations, but it is possible, right. So, you can actually identify what is this value, and then I can use this to get these values, right, but it is all possible, it is all mathematics, right. And this is being demonstrated in this work recently, that with scan chain you can actually get your, it is much easier to attack, right, because in powered side channel you are assuming that I do not have the access to these values, right, this output, but here because of scan chain I have access to these values, and it will be much easier, just some mathematical calculation equations you will solve it, you do not need any powered side channel anything, just you control the inputs and it will give you the outputs. Okay. Any question? So, this is very powerful attack, right, it can break your weights very quickly, right. So far we have not seen much counter measures, we propose couple of them, I will talk about that. So, how do you protect it, you say, I will not go into solution, let us see. You have this access to this point, right, scan chain, you cannot stop that because that is designed for test, right. How can I stop that? So, that means attacker still access this value, but still he cannot get the weights. What are the things I can do? Any suggestion? We come up with 2 suggestions, I will talk about that, but before that I want to you to propose something. Yeah.
Sir, one is that the access to the scan chain should be through some kind of authorization. Nobody else should be able to.
Yeah,
take.
understood, but basically you give the contact to some test facility, right. Some test facility is coming in Gujarat, sorry, in Guwahati now, right, and there may be some dishonest person there. So, you have an agreement that you test me and I authorize you to test, and one of the 200 people is not honest, right, he does this, right. So, this always happen, and this is because so many things get leaked and all, right. But what kind of modification I can do, so that even if I give you, you will not able to get. Shares is one thing I have talked about. Yeah, shares is one solution, that you now you get kind of random values, right. So, you will not get that. That is one of the solution. That protection, whatever I talked about on this masking, that also kind of gives some protections. That is good. So, good solution. Any other solution? Lightweight masking is heavyweight solution, right. Can I have some lightweight solution? Anybody? It is a long day, some thoughts at the end of the day. Philosophy is that you still have the access at this point, but he will not get what weight is being used there. Can I obfuscate or hide the weight? Right. So, if he does not know whether it is a WI or this, he will not able to make out, right. Okay. So, maybe I will talk about the solution. Sorry, use the mic.
Like by encrypting the weights.
Encrypt the weights, okay. But if you encrypt, then your computations has to be also on the encrypted domain, right, that is homomorphic encryption or something.
Yeah.
So, you cannot do multiplication, right, because 5 is encrypted to 70.
Yeah, yes sir.
So, then the multiplication has to be done on encrypted data. So, that is a different ballgame, right, but a good try. Yeah, at least I got 2 solutions, which I not thought, I do not thought about. Okay, good. Any other? We thought about two solutions, one is good, one is bad, and I got two solutions from here, which is good. Okay, let us move on. So, the first solution we talked about that, how about retrain the model with you add a key in your data set. Okay. Suppose you are basically having a 16-bit data input and output is some classification, say 0 of 2 bits, okay, and you train that neural network on this data set. What I am going to do it now, whatever the data, I will just add a 32-bit key here. Okay. So, your data set now become 48 bits, and then I retrain the model. I will get a different model now, not the same model, it will give a different weights and biases. Okay. And then when I sell this to the market, I will put this key into some tamper-proof memory which is inside the chip, okay, and then I will send it to the market. So, from the user perspective there is no key, right, they will still give the 16-bit input, they will get the 2-bit output. Okay. But when I give to the test, I will not give this. This is basically the final product, right. I will only give them to test this. So, since they do not know the key, they will augment some arbitrary key and that will be given there, and ideally the accuracy should be or the prediction should be incorrect, because the key that you have added is not there. So, if you give an arbitrary key value, it will effectively not predict or classify correctly. Make sense? But this has a cost because you have to retrain again, right, and training process may takes time, right. So, this is one solution, but may not be very good solution. Without retraining, if you can do that will be best, right. Understood? You understand how it will protecting the weights? Even if you get that, because your this data is not there, you get all incorrect. So, you cannot control your input. So, what you are doing, try to say that you are doing Wi into Xi, but the entire Xi is not available to you. So, you do not know what is Wixi. So, from Wixi you will not able to make out what is the Wi, because you do not know part of Xi, right. This Xi is now 32 bits, 32 plus 16, you have only access to this 16 bits, other 32 bits you do not have access. So, if you give something, you will not know what is the outcome, right. So, that is the kind of idea. Okay. So, this is one solution we thought of. The second one is interesting. What we did is basically we add few dummy nodes, okay, and we obfuscate these interconnections, right. We obfuscate these interconnections. We will not tell you whether this node is multiplying with this or this node is multiplying with this, and it is basically for not fully connected network. If it is fully connected, everything is getting multiplied, right. So, the idea is very simple, that I would add a mux here, multiplexer, and whatever the input node, I will connect all of them, and there is a key that will select the correct input, right. So, then there is this is Wi, right. So, I do not know which Xi will getting multiplied with Wi, right, and same thing in every process, and I use different key. So, here maybe the correct value is 0 0, here it may be 1 0, it is maybe 1 1 here, here maybe 1 1. So, total key size become 2 bit 8 bits, and they will pick the correct values, right. So, now if you give this network, if you have access to this, because you are doing Wi into Xi, you are doing this, but you do not know which Xi is getting multiplied with which, right. So, you will not able to control which particular input to will give non-zero and other 0, right. So, it will basically you need kind of exponential try to give to identify the correlation. Understood? Clear? So, this we did, and this is what is our tool. If is basically if you give a train network, it will add this key and it will give you this obfuscation of these interconnections, and then if you use this HLS for ML or our LHS, it will give you the RTL, right. So, that you will get the RTL basically. So, we have some experiment that if you give wrong key, how it is impacting, and it is very interesting to see that if you have say this model we have used, there are 5 layers, actual accuracy was some 96%, and I have just used only say 8-bit key, okay. And if you lock the last layer, the 5th layer, if you just give 2 bit wrong, your accuracy becomes 62%. So, almost 35% drop in the accuracy, right. If you make 4 bit change, accuracy become 34, which is basically useless model, right. So, from 96 become 34. Similarly, whenever you have say 8 bit, if you lock the first layers, 2 bit only dropping is 1%, right. If you change 4 bits, dropping is only 4%. So, what it suggests? That you should lock the last layers, right, because in the last layer if you even lock 2 bits, I mean if you just give 2 wrong bit is 30% regression in the accuracy. Here it is only 1% or 3%, and this was consistent for every model we tried. So, the takeaway from this, that when you try to lock, you do not need to lock the entire model, you take the last layer and more lock there, right. So, if you lock or obfuscate that layer, even if you give 1-2 bit also wrong key, your accuracy will be significantly drop and the model will be useless. And since during testing I will not give you the correct key, so it is basically useless model, you will not able to get anything. Your prediction is itself wrong, right. So, you will not able to use it. Okay, so, that is all, and we have shown that we did experiment, and we basically, so that because we are only adding 1 mux layer, 2 mux layer in the entire circuit, it has a lot of multiplier and all. So, obviously area overhead is insignificant, not even 1%, right, and it is just adding the delay of 1 multiplexer. So, delay is also very less, overhead is also less, not even 1%, right. So, it is a good solution effectively. Okay, so, that is this is basically on the solution we talked about. We basically this is one solution. The other one is that the future direction I was talking about, we are locking the network. So, there are lot of work in the research community, how do you lock this scan chain also. Okay. I mean it is well known that thread that through scan chain you can do many kind of attacks. So, there are many way you can actually lock the scan chain, and one of the recent work is called dishonest oracle. It basically says that whenever you try to access the scan chain in, it will basically give a wrong key, so that you will not basically get your correct scan chain, right. It will basically arbitrary values, right. So, as a result you can actually use scan chain in the functional mode or testing mode, only if you are authorized, then only you will be able to do that, right. So, basically just to give you the idea here is that if the scan enable, so there is a specific value, give it to scan enable, whenever it is giving 1, it will select this wrong key, right, and this is your lock design, or this one it will basically get wrong keys, right. That is basically a 2 layer protection, that you try to lock the scan chain as well as lock the design, and make sure that if you try to access my scan chain, it will give you wrong key, but testing will be still done, right. And then you might question me that how the testing will be done. I know that if this is the wrong key I give, what is the corresponding output. So, he do all this test and he will get the wrong key, not the correct key, because he will still get the weights, but that will be the wrong key, not the correct key, right. So, this is where my testing will be done, and I can stop that guy to get the correct keys, right. This is how the idea of this, but this can be done in future. Okay. So, in conclusion, in today's discussion we talked about various possible attacks on machine learning hardware, and then we talked about few solutions for both kind of this scan chain and power side channel attacks based solutions, right. One solution is basically the masking, but masking has lot of intricacies here, is not straightforward application as we discussed. On the other hand, for scan chain you need to obfuscate the interconnections and also obfuscate the scan chain, and combining them will give the best solution. Okay. So, that is all for the day. Thank you. So, we will conclude here today, and tomorrow we will continue again from 10 a.m. Okay. Thank you.